This e-text is otherwise provided to you, as is no other. Warranties of any kind, express or implied, are made to you as to the e-text or any medium it may be on, including but not limited to warranties of merchantability or fitness for a particular purpose. Some states do not allow disclaimers of implied warranties or the exclusion or limitation of consequential damages, so the above disclaimers and exclusions may not apply to you, and you may have other legal rights. Indemnity: you will indemnify and hold the project, its directors, officers, members, and agents harmless from all liability, cost, and expense, including legal fees, that arise directly or indirectly from any of the following that you do or cause: 1. Distribution of this e-text, 2. Alteration, modification, or addition to the e-text, or 3. Any defect. Distribution under Project Gutenberg TM. You may distribute copies of this e-text electronically, or by disc, book, or any other medium if you either delete this small print and all other references to Project Gutenberg, or 1. Only give exact copies of it. Among other things, this requires that you do not remove, alter, or modify the e-text or this small print statement. You may, however, if you wish, distribute this e-text in machine-readable binary, compressed, markup, or proprietary form, including any form resulting from conversion by word processing or hypertext software, but only so long as either *, the e-text, when displayed, is clearly readable, and does not contain characters other than those intended by the author of the work, although tilde, asterisk, and underline, underscore, characters may be used to convey punctuation intended by the author, and additional characters may be used to indicate hypertext links, or asterisk. The e-text may be readily converted by the reader at no expense into plain ASCII, EBCDIC, or equivalent form by the program that displays the e-text, as is the case, for instance, with most word processors, or asterisk. You provide, or agree to also provide on request at no additional cost, fee, or expense, a copy of the e-text in its original plain ASCII form, or in EBCDIC or other equivalent proprietary form. 2. Honor the e-text refund and replacement provisions of this small print statement. 3. Pay a trademark license fee to the project of 20% of the net profits you derive, calculated using the method you already used to calculate your applicable taxes. If you don't derive profits, no royalty is due. Royalties are payable to Project Gutenberg Association / Carnegie Mellon University within the 60 days following each date you prepare, or were legally required to prepare, your annual, or equivalent periodic, tax return. What if you want to send money even if you don't have to? The project gratefully accepts contributions in money, time, scanning machines, OCR software, public domain e-texts, royalty-free copyright licenses, and every other sort of contribution you can think of. Money should be paid to Project Gutenberg Association / Carnegie Mellon University. And the small print. For public domain e-texts *ver. 0.04.29.93 and *. Scanned by Charles Keller with OmniPage Professional OCR software. TB is a triple bond. Dot is a dotted coordinated bond. Emphasis. Italics have a * mark. Hashtag. Footnotes move to year paragraphs but not renumbered. They are numbered A or B when two pages of notes are together. Comments and guessed at characters in braces need stripped / fixed. Greek letters are encoded in GR brackets, and the letters are based on Adobe's symbol font. Organic Syntheses, an annual publication of satisfactory methods for the preparation of organic chemicals. Editorial Board. James Bryan Conant, Editor-in-Chief. Hans Thatcher Clark, Roger Adams, Oliver Combe. Contributors: H. Coleman, J. C. Hessler, P. Kohler, C. S. Marvel, W. A. Noyes, G. R. Robertson, E. B. Vliet, F. C. Whitmore, Volume 2. Caveat: some numbers did not OCR correctly and may not have been corrected during the proofing. Check the 1941 print edition before trying these. Introduction to the series. The publication of this series of pamphlets has been undertaken to make available in a permanent form complete detailed directions for the preparation of various organic chemical reagents. In announcing this purpose, it may be well to mention at the outset some of the difficulties in the way of the research chemist, which it is hoped this series will be able to overcome. The cost of chemicals is prohibitive to the majority of chemists. This was true before the war when Kahlbaum's complete supply was available, and today, with our dependence on domestic stocks, this cost has increased. The delay in obtaining chemicals, especially from abroad, even if the expense need not be considered, is an important factor. These difficulties have therefore thrown the research chemist on his own resources. The preparation of materials for research, always time-consuming and annoying, is made increasingly so by the inexactness of the published information which so often omits essential details. Because of this, much needless experimentation is necessary in order to obtain the results given in the published reports. As the additional information thus acquired is seldom published, duplication of such experiments occurs again and again, a waste of time and material. It is hoped these difficulties may be remedied by the publication of this series of pamphlets. In other words, the authors hope to make this a clearing house for the exchange of information as to methods of preparation of some of the most needed organic chemical reagents. On account of the impossibility of obtaining the less common organic chemicals in the United States during the past few years, university laboratories have had no option but to prepare their own supplies. At the University of Illinois, for instance, a special study has been made of this field, and methods for the production of various substances have been investigated. As a result, reliable methods and directions have been developed for producing the materials in 1/2 to 5 pound lots. Such work as Illinois has done is now being given an even more extensive scope at the research laboratory of the Eastman Kodak Company. It is felt that the results from these various laboratories should be available to all chemists, and it is hoped that they eventually will be completely incorporated in these pamphlets. The organic chemicals herein discussed have been quite arbitrarily chosen, being those which have been needed in various research laboratories in the last years and for which the directions happen now to be ready for publication. The methods are in only a few cases new ones. They are in general the most satisfactory to be found in the literature. Only such details have been added as will enable a man with a reasonable amount of experience in organic chemistry to duplicate the results without difficulty. To be absolutely sure that each set of directions can be repeated, every experiment has been carried out in at least 2 laboratories. Only after exact duplication of the results in both laboratories are the directions considered ready for publication. The names of the chemists who have studied the various experiments are given so that further information concerning any obscure point can be obtained if any question arises in using these directions. And finally, in describing the experiments, special attention has been given to the explanation of why it is necessary to follow the directions carefully, and what will happen if these directions are not followed. Although the main object in this series is to give the most convenient laboratory methods for preparing various substances in 1/2 to 5 pound lots, an attempt has also been made to have these processes as far as possible adaptable to large-scale development. For example, extractions have been avoided wherever possible, cheap solvents have been substituted for expensive ones, and mechanical agitation, a procedure extremely important in the success of many commercial processes, has usually been specified. The apparatus used is always carefully described, and wherever necessary an illustration is given. Accompanying each preparation there will be found a bibliography containing references to all the methods for the production of the substance described in the literature. This is given in order to aid any future investigator who may wish to study or improve the methods of preparation. It is not claimed that the methods are, in every case, completely perfect, but only that the yields are very satisfactory and allow the production of the substances at a reasonable cost. It is hoped, therefore, that the pamphlets will benefit not only the scientific research man of the university, but also the technical chemist who desires to develop the preparation of one of these substances to a large-scale process of manufacture. The editors trust also that this work may be used to advantage as a preparation manual in intermediate or advanced courses in organic chemistry in university laboratories, and that it will aid small colleges in the production of necessary reagents which they are often financially unable to purchase. The pamphlets are to be edited by the following committee: Roger Adams, University of Illinois, Urbana, Illinois; J. B. Conant, Harvard University, Cambridge, Massachusetts; H. T. Clark, Eastman Kodak Company, Rochester, New York; Oliver Combe, Park, Davis Company, Detroit, Michigan, each to act for 1 year as editor-in-chief and the other 3 to assist him as associate editors. A new number of the series will appear annually, and every 5 years the data will be rearranged, revised, corrected, and then published in book form. The number of preparations to be completed yearly is not fixed. There will be, it is certain, about 20, and it is hoped, as the interest is stimulated in this work, that this number may increase considerably. The editors especially desire to solicit contributions from other chemists, not only in this country but abroad. Whenever a compound is thoroughly and extensively studied in connection with some research, it is hoped that complete directions for its preparation will be assembled and sent to the editor. He will then have them checked and published in a subsequent number. Directions for the preparation of substances already on the market are needed to make this work complete, and will be gladly accepted. It will, of course, be recognized that an occasional mistake or omission will inevitably be found in such a pamphlet as this, which contains so many references and formulae. The Committee on Publication will therefore deem it a favor if they are notified when any such error is discovered. It is hoped also that if any chemist knows a better method for the preparation of any of the compounds considered, or if anyone discovers any improvements in the methods, he will furnish the authors with such information. Any points which may arise in regard to the various preparations will be gladly discussed. In conclusion, the editors are ready to do all they can to make this work successful, and welcome suggestions of any kind. They feel that the success of the series will undoubtedly depend upon the cooperation of others, and as its success promises to be important to research chemists, the editors urge all interested to assist. The editors. Table of Contents, page I. Benzylacetophenone, 1-2. Benzobenzoate, 5-3. Benzyl cyanide, 9-4. A. G-dichloroacetone, 13V.P-dimethylaminobenzaldehyde, 17-6. Ethyl oxalate, 23-7. Ethyl phenylacetate, 27-8. Glycerol A. G-dichlorohydrin, 29-9. Glycerol A monochlorohydrin, 33X. Hydrazine sulfate, 3711. Mesitylene, 4112. Methyl red, 4713.P-nitrobenzoic acid, 5314.P-nitrobenzylcide, 5715.P-nitrophenylacetic acid, 5916. Nitrosobenathyl, 6117. Phenylacetic acid, 6318. Phenylacetylene, 6719. Phenylhydrazine, 71XX. Phthalimide, 7521. Quinoline, 7922. Quinone, 8523. Sodium toluenosulfonate, 8924. 1,3,5-trintrobenzene, 9325. 2,4,6-trintrobenzoic acid, 95 index, 99 organic syntheses I-benzylacetophenone. C6H5CHO plus C6H5 COC3 plus, NAO, C6H5CH equals COC6H5 plus H2O. Prepared by E. P. Kohler and E. M. Chadwell. Checked by H. T. Clark and R. P. Levitt. 1. Procedure. A solution of 218 g of sodium hydroxide and 1960 g of water and 1000 g of 95% alcohol are introduced into a 5,500 cubic centimeters bottle, which is loosely covered with a perforated disc of cardboard, supplied with an effective stirrer, and supported in a larger vessel so as to permit cooling with cracked ice. Into the alkaline solution, 520 g of pure acetophenone is poured. The bottle is rapidly surrounded with cracked ice, and the stirrer started. 460 g of benzaldehyde U.S.P. are then added at once. The temperature of the mixture should not be below 15 feet 0 inches, and it should not be allowed to rise above 30 feet 0 inches during the reaction. If it tends to do so, the stirring is not sufficiently vigorous. It is advantageous, though not essential, to inoculate the mixture with a little powdered benzylacetophenone after stirring for half an hour. After 2 to 3 hours, the mixture becomes so thick that the stirring is no longer effective. The stirrer is then removed and the mixture left to itself in an icebox for about 10 hours. The mixture now is a thick paste composed of small shot-like grains suspended in an almost colorless liquid. It is cooled in a freezing mixture and then either centrifuged or filtered on a large Buchner funnel, washed with water until the washings are neutral to litmus, and finally washed with 200 cubic centimeters of alcohol, which has previously been cooled to 0 feet 0 inches. After thorough drying in the air, the crude product weighs about 880 g, yield 97% of the theoretical amount, and melts at 50-54 foot 0. It is sufficiently pure for most purposes but tenaciously holds traces of water. It is most readily purified by recrystallization from 4 to 4.5 times its weight of 95% alcohol. 880 grams of crude product gives 770 g, 85% of the theoretical amount, of light yellow material, M.P., 55-57 foot 0, and 40 to 50 g, that require recrystallization. 2. Notes. The acetophenone should be as pure as possible, M.P., 20 feet 0 inches. Commercial acetophenone contains variable quantities of impurities which reduce the yield. By distilling commercial acetophenone with the help of a good stillhead, preferably under diminished pressure, and using only the fraction which boils at 201-202 foot 0, 76-770/10 mm, greater quantities of benzylacetophenone can be obtained than by using the entire sample. Commercial benzaldehyde can be used in place of the purer product, but the amount used must be increased to make up for the impurities which are present. If the temperature is too low, or the stirring too slow, the product separates as an oil, which later solidifies in large lumps. If the temperature is allowed to rise above 30 feet 0 inches, secondary reactions diminish both the yield and the purity of the product. The most favorable temperature is 25 feet 0 inches. In recrystallizing benzylacetophenone, the alcohol should be saturated at 50 feet 0 inches. If the solution is saturated above this temperature, the benzylacetophenone tends to separate as an oil. The solution should be allowed to cool gradually, and should finally be chilled in a freezing mixture. 3. Other methods of preparation. The methods for producing benzylacetophenone are the action of acids on a mixture of benzaldehyde and acetophenone or on a solution of these substances in glacial acetic acid (1), the condensation of benzaldehyde and acetophenone with a 30% solution of sodium methylate at low temperatures (2), the action of sodium hydroxide on an alcoholic solution of benzaldehyde and acetophenone. 3. The methods based on the use of acids as condensing agents were not considered, because Claisen, who devised them, abandoned them after he found that alkaline condensing agents gave better results. The preliminary experiments showed that condensation with sodium methylate takes a long time and gives a product which it is difficult to handle in large quantities. The method devised by Kostenecki and Rossbach 3 has therefore been developed. 1 Br. 14, 2463, 1881. 2 Br. 20, 657, 1887. 3 Br. 29, 1492, 1896. 2 benzoate. 2 C6H5 CHO plus C6H5 CH2 ONA. C6H5 CO2 CH2 C6H5 plus C6H5 CH2 ONA. Prepared by O. Com and W. F. Com. Checked by Roger Adams and R. L. Jenkins. 1. Procedure. 3 grams of metallic sodium are dissolved by warming for half an hour in 70 g of pure benzyl alcohol, see notes, and after the mixture has cooled to room temperature the solution is added gradually, with thorough mixing, to 454 g of C.P. benzaldehyde, which must contain less than 1% of benzoic acid. The reaction mixture has a tendency to become warm, but the temperature should be kept slightly below 50-60°C by cooling, if necessary. A pasty gelatinous mass results. After about half an hour, the temperature of the mixture no longer rises. It is then warmed on the water bath for about 1 or 2 hours, with occasional shaking. The cooled reaction product is treated with 200 cubic centimeters of water, the layer of oil separated, washed once with a second portion of water, and subjected to distillation in vacuo. The first fraction of the distillate contains benzyl alcohol together with unchanged aldehyde, as well as a small quantity of water. The temperature then rises rapidly to the boiling point of benzyl benzoate, when the receivers are changed. The product boils at 184-185 foot 0/15 mm. An analysis by saponification shows it to consist of 99% ester. A yield of 410 to 420 g is obtained, which corresponds to 90 to 93% of the theoretical amount. This benzyl benzoate supercools readily, but after solidifying melts within 1 degree of the highest recorded value, 19.4 feet 0 inches, and therefore need not be refractionated, unless material of exceptional grade is required. 2. Notes. In the presence of sodium benzylate, 2 molecules of benzaldehyde react with the alcoholate to form an addition product. When the reaction mixture is overheated, an important side reaction may occur, as follows. Oct2C6H5C6H5C, Oct2C6H5, C6H5 Co2 Na plus C6H5CH2 Oct2C6H5 \ONA. Dibenzyl ether no doubt forms the chief impurity in benzyl benzoate. Since the boiling point of the former lies near that of the ester, it is not removed during the process of purification by distillation. The causes of variations in yield by the use of the older methods can now be explained. When benzaldehyde is added to the alcoholate, and especially when the latter is still warm, local overheating results. In fact, the temperature may rise far above 100 feet 0 inches with the result that benzyl ether is formed. Simultaneously, the sodium benzylate is converted into sodium benzoate, which is of no value for inducing the desired reaction, and consequently very little benzyl benzoate is obtained. The same side reactions explain the failure of this experiment when the benzyl alcohol used in preparing the catalyst, sodium benzylate, is contaminated with benzaldehyde. The benzyl alcohol used in this preparation must be free from impurities, especially aldehyde. 1 cc dissolved in 50 cubic centimeters of water and treated with a freshly prepared clear solution of phenylhydrazine acetate should give no appreciable precipitate. If it is not pure, it must first be treated with alkali as described below. The benzaldehyde should be titrated in order to determine its acidity. If it is found to contain sufficient benzoic acid to react with a considerable proportion of the sodium alcoholate, a poor yield of ester will be obtained. Less than 1% of benzoic acid will not interfere seriously with the yields obtained, but the presence of larger quantities of acid will be found to be detrimental and must be removed by washing the benzaldehyde with a sodium carbonate solution and redistilling with the precautions necessary to prevent too free an access of air to the distillate. The order of mixing the reagents and the temperature of the ingredients at the time of mixing are the most important factors in the experiment. The temperature at which the reaction mixture is maintained after mixing, provided that it is held below 100 feet 0 inches, is less important from the standpoint of purity. The reaction mixture is not treated with acetic acid, as usually recommended, for the reason that such a procedure yields a final product contaminated with benzoic acid, unless an alkaline wash is applied subsequently. The recovered benzyl alcohol can be used for the preparation of a second lot of benzyl benzoate only after it has been boiled with strong sodium hydroxide to remove all traces of benzaldehyde. 3. Other methods of preparation. Benzyl benzoate has been identified in certain natural plant products. 1. In the laboratory it has been prepared by the action of a. benzyl chloride upon benzyl alcohol, 2. b. benzyl chloride upon sodium benzoate, and c. alcoholates upon benzaldehyde. 3. Recently, Gomberg and Buckler, 4. have shown that reaction b. may be conducted even with aqueous solutions of sodium benzoate. 1 and 152, 131, 1869. 2. Gmelins Handbuch der Organ. Chem. 340. 3 Br. 20, 649, 1887. Cf. also J. Chem. SOC 75, 1155, 1899. 4 J. M. Chem. SOC 42, 2059, 1920. The Claisen method C furnishes the most convenient and practical procedure for the preparation of this ester. The materials are cheap, the experimental procedure simple, and the product obtained is free from objectionable traces of benzyl chloride. Unfortunately, the method has been found to be extremely erratic in regard to yield, 10 to 95%, as well as in regard to purity of the product, 87 to 97% ester. 1. As a result of the present study, 2. Causes for variations are fully accounted for and the procedure has been converted into a satisfactory method of preparation. 1 C. A. 14, 3500, 1920. 2 J. M. Farm. Associate 11, 599, 1922. 3 benzyl cyanide. C6H5CH2Cl plus NaCN. C6H5CH2Cn plus NaCl. Prepared by Roger Adams and A. F. Thel, checked by O. Com and A. O. Matthews. 1. Procedure. In a 5L. round-bottom flask, fitted with a stopper holding a reflux condenser and separatory funnel, are placed 500 g. of powdered sodium cyanide, 96 to 98% pure, and 450 cubic centimeters of water. The mixture is warmed on a water bath in order to dissolve most of the sodium cyanide, and then 1 kilogram of benzyl chloride B, P, 170-180 foot 0, mixed with 1 kilogram of alcohol is run into the separatory funnel in the course of 1/2 to 3/4 of an hour. The mixture is then heated with a reflux condenser on the steam bath for 4 hours, cooled and filtered with suction to remove most of the sodium chloride. It is well to wash the filtered salt with a small portion of alcohol in order to remove any benzyl cyanide which may have been mechanically held. The flask is now fitted with a condenser, and as much alcohol as possible is distilled off on the steam bath. The residual liquid is cooled, filtered if necessary, and the layer of benzyl cyanide separated. This crude benzyl cyanide is now placed in a Claisen distilling flask and distilled in vacuo, the water and alcohol coming over first, and finally the cyanide. It is advantageous to use a fractionating column or, better still, a Claisen flask with a modified sidearm 1, Volume 1, page 40, Figure 3, which gives the same effect as a fractionating column. The material is collected from 135-140 foot 0/38 mm, 115-120 0/10 mm. The yield is 740 to 830 g, 80 to 90% of the theoretical amount. 1 J. M. Chem. SOC 39, 2718, 1917. 2. Notes. The quality of the benzyl chloride markedly affects the yield of pure benzyl cyanide. If a poor technical grade is used, the yields will not be more than 60 to 75% of the theoretical, whereas consistent results of about 85% or more were always obtained when a product was used that boiled over 10 feet 0 inches. The technical benzyl chloride at hand yielded on distillation about 8% of high boiling material. A technical grade from another source was of unusual purity and boiled over a 2 feet 0 inches range for the most part. It is advisable to distill off the last portion of alcohol and water in vacuo and also to distill the benzyl cyanide in vacuo, since under ordinary pressures a white solid invariably separates during the distillation. One method of purifying the benzyl cyanide is to steam distill it after the alcohol has been first distilled from the reaction mixture. At ordinary pressures, this steam distillation is very slow and, with an ordinary condenser, requires 18 to 20 hours in order to remove all of the volatile product from a run of 500 g of benzyl chloride. The distillate separates into 2 layers. The benzyl cyanide layer is removed and distilled. The product obtained in this way is very pure and contains no tarry material, and after the excess of benzyl chloride has been removed, boils practically constant. This steam distillation is hardly advisable in the laboratory. The benzyl cyanide, prepared according to the procedure as outlined, is collected over a 5 feet 0 inches range. It varies in appearance from a colorless to a straw-colored liquid and often develops appreciable color upon standing. For a product of special purity, it should be redistilled under diminished pressure and collected over a 1-2 foot 0 range. For most purposes, such as the preparation of phenylacetic acid or ester, the fraction boiling 135 to 140 foot 0/38 mm point is perfectly satisfactory. 3. Other methods of preparation. Benzyl cyanide occurs naturally in certain oils. 1. The only feasible method of preparing it that has been described in the literature is the one in which alcoholic potassium cyanide and benzyl chloride, 2, are employed. The cheaper sodium cyanide is just as satisfactory as the potassium cyanide and therefore is the best material to use. Gomberg has recently prepared benzyl cyanide from benzyl chloride and an aqueous solution of sodium cyanide. 3. 1 Br. 7, 519, 1293, 1874, 32, 2337, 1899. 2 and 96, 247, 1855, Br. 3, 198, 1870, 14, 1645, 1881, 19, 1950, 1886. 3 J. M. Chem. SOC 42, 2059, 1920. 4. A. G-dichloroacetone. CH2 Chalk 2 Cl plus O, Na 2 Cr2O7 plus H2SO4, CH2 Chalk 2 Cl plus H2O. Prepared by J. B. Conant and O. R. Quayle. Checked by A. W. Dox L. Yoder and O. Com. 1. Procedure. In a 2L flask are placed 375 g of commercial sodium dichromate, 225 cubic centimeters of water, and 300 g of dichlorohydrin B, P, 68-75 foot 0/14 mm. The flask is set in a water bath and equipped with a thermometer and mechanical stirrer. The contents are vigorously stirred, and 450 g of sulfuric acid diluted with 115 g of water are introduced during the course of 7 to 8 hours. It is convenient to add the acid at 10-minute intervals. The temperature is kept between 20 feet 0 inches and 25 feet 0 inches during the entire reaction. This is accomplished by adding a little ice to the water bath from time to time. The stirring is continued for 16 to 17 hours after all the acid has been added. As there is very little heat evolved during this part of the reaction, the water bath may be allowed to come to room temperature. Sufficient water is now added to the mixture to dissolve the pasty chromium salts, 300 to 800 cubic centimeters. The mass of crystals is then rapidly filtered on a Buchner funnel and sucked as dry as possible. The crystals are then transferred to a small laboratory centrifuge and centrifuged for several minutes. The crystals are washed in the centrifuge with about 15 to 25 cubic centimeters of ice water, then with 10 to 15 cubic centimeters of cold petroleum ether, and finally centrifuged till as dry as possible. The crude dichloroacetone is dried in a vacuum desiccator over sulfuric acid overnight. It weighs about 220 g. The crude product is best purified by distillation from a 250 cubic centimeters distilling flask fitted with an air condenser. A very small fraction, 10 to 15 g, of low boiling material is obtained, and the dichloroacetone, 170-175 foot 0, is then collected. It solidifies in the receiver to a white crystalline mass which weighs 200 to 220 g, 65 to 70% of the theoretical amount. A few grams more may be obtained by chilling the low boiling fraction and filtering off the water. 2. Notes. Great caution should be exercised in working with dichloroacetone, as it is extremely lacrimatory and blisters the skin. In transferring the crystals from the reaction flask to the Buchner funnel, it is necessary to use a certain amount of water to dissolve the pasty chromium salts, which are otherwise quite impossible to filter. The amount necessary varies greatly in different runs, according to the manner in which the chromium salts separate. The amount of this water is kept low in order to dissolve as little of the product as possible. Nevertheless, 10 to 15 g of dichloroacetone are thus dissolved. This material, together with a little unchanged dichlorohydrin, may be recovered by a long procedure involving extraction with ether and sodium bisulfite. This is not profitable, however. It is not necessary to wash the crystals in the centrifuge until they are white. A small amount of chromic salt will not interfere with the subsequent purification. Commercial sodium dichromate is hygroscopic and contains varying amounts of water. The 375 g required in these directions are equivalent to 319 g of anhydrous material. The total time required for the oxidation is 24 hours. It is convenient to start the reaction in the morning. In this way, the last part of the reaction, which requires no attention, will be accomplished during the night. The regulation of the temperature is necessary, as the reaction proceeds very slowly below 20 feet 0 inches. On the other hand, the dichloroacetone itself is oxidized at a somewhat higher temperature than 25 feet 0 inches. 3. Other methods of preparation. The preparation of dichloroacetone by the following methods is described in the literature: the direct chlorination of acetone Winkwitherfraun 1, the oxidation of dichlorohydrin Winkwitherfraun 2, the action of silver chloride on diodoacetone Winkwitherfraun 3, the action of dichloropropene, CH2ClCCl equals CH2, and hypochlorous acid Winkwitherfraun 4, the action of hydrochloric acid on ethoxymonochloroacetoacetic ester Winkwitherfraun 5, and the hydrolytic cleavage of dichloroacetoacetic ester. 6. 1 Jars. 1859, 345, 1871, 531, J. Pracht. Chem. 2 4, 52, 1871, Br. 7, 467, 1874, 8, 1330, 1438, 1875, 26, 598, 1893, 42, 3233, 1909, and 279, 315, 1894. 2 Br. 6, 1210, 1873, 13, 1706, 1880, 42, 3233, 1909, and 208, 355, 1881, 269, 46, 1892, and Chim. Phys. 6, 9, 145, 1886, Bull. SOC Chim. 2, 36, 19, 1881. 3, and 192, 93, 1878. 4, Comptroller Rend. 94, 1428, 1882. 5, and 269, 18, 1892. 6 Br. 43, 3533, 1910. V. P-dimethylaminobenzaldehyde. CH3, 2NC6H5 plus NO2, CH3, 2NC6H4 NO plus H2O, CH3, 2NC6H4 NO plus 2CHO plus 2C6H5N, CH3, 2, CH3, 2NC6H4N equals CHC6H4N, CH3, 2 plus 2H2, plus, CH3, 2NC6H4CHO, CH3. 2NC6H4N equals CHC6H4N, CH3, 2 plus CHO, CH3, 2NC6H4N equals CH2 plus, CH3, 2NC6H4CHO. Prepared by Roger Adams and G. H. Coleman. Checked by H. T. Clark and W. W. Hartman. 1. Procedure. In a 3L. Round-bottom flask fitted with a mechanical stirrer 150 g of technical dimethylanilin are dissolved in 750 cubic centimeters of diluted hydrochloric acid, 1 part concentrated acid to 1 part water. This solution is now cooled to 0 feet 0 inches, and a solution, previously cooled to 0 feet 0 inches, of 90 g, of technical sodium nitrite in 150 cubic centimeters of water is added through a separatory funnel. During the addition of the nitrite solution, mechanical stirring should be employed and the flask cooled well with ice and salt. The addition is made at such a rate, 30 to 40 minutes for the entire addition, that the temperature does not rise above 5 feet 0 inches. The precipitate of nitrosodimethylanilane hydrochloride is filtered off with suction, then washed with about 300 cubic centimeters of diluted hydrochloric acid, 1:1. In a 2L beaker, 180 g of technical dimethylanilane, 125 cubic centimeters of formaldehyde, technical 40%, and 300 cubic centimeters of concentrated hydrochloric acid are mixed and heated for 10 minutes on a steam bath. The mixture is now placed in a hood and the nitrosodimethylanilane added all at once, or as rapidly as possible. The beaker is then covered with a watch glass. A vigorous reaction soon occurs and is complete in about 5 minutes. The resulting solution is transferred to a 5L flask and diluted to 4L. Stirring is started, and a 25% solution of sodium hydroxide is added until the red color disappears. About 650 cubic centimeters are required. The yellow benzylidine compound separates, is filtered with suction and washed with water. The moist precipitate is transferred to a 4L glass jar, covered with 1,000 cubic centimeters of 50% acetic acid and 250 cubic centimeters of formaldehyde, and stirred until 20 minutes after the benzylidine compound has gone into solution. While the mixture is being stirred vigorously to prevent lumping of the precipitate, 400 cubic centimeters of water and 200 g of cracked ice are added during the course of 5 minutes. The dimethylamino-benzaldehyde generally separates gradually in 15 to 20 minutes, but in some cases does not. If the precipitate does not form, the solution is placed in a refrigerator for a few hours or overnight. The mixture is filtered with suction and washed at least 10 times with 300 cubic centimeters of water. The precipitate is sucked as dry as possible for 15 to 30 minutes. The slightly moist aldehyde is distilled under diminished pressure from an oil bath, by means of a 1L Claisen flask. A small amount of water comes over first, then the thermometer rises rapidly to the boiling point of the aldehyde, 180/22 mm point. In changing receivers between the water fraction and the aldehyde, care should be taken to keep the sidearm of the distilling flask warm. Otherwise, on starting the distillation again, the aldehyde will solidify in the sidearm and cause trouble. It is advisable not to collect the very last portion of the distillate with the main portion, as the former is frequently quite red. This is best added to crude material from another run. The main distillate is dissolved in 100 cubic centimeters of alcohol in a 2L beaker, then 1,000 cubic centimeters of water are gradually added with vigorous mechanical stirring to prevent lumping. The aldehyde separates and is filtered with suction. The product, when dry, weighs 125 to 130 g, 56 to 59% of the theoretical amount, and melts at 73 feet 0 inches. The aldehyde prepared in this way is in the form of small granular crystals, which vary in different runs from a flesh color to a lemon yellow. For practically all purposes, this slightly colored product is entirely satisfactory and is essentially pure, as can be judged by the melting point. For reagent purposes, it is desirable to remove the color completely, particularly since the product obtained as just described has a tendency to take on a reddish tinge on exposure to light. Further purification can be accomplished by dissolving the aldehyde. It dissolves slowly in dilute hydrochloric acid, 1 part of concentrated acid, SPGR 1.19, to 6 parts of water, 125 g, of aldehyde requiring 700 cubic centimeters of the acid. The solution is placed in a jar and diluted with half its volume of water, and dilute sodium hydroxide solution, 15 to 20%, is added slowly with mechanical stirring. At the beginning, the aldehyde comes down slightly colored. after about 10 to 30 G, are precipitated. However, the product appears white. This point can be readily seen. The first precipitate is filtered off and added to the next run of crude material, or fractionally precipitated again from hydrochloric acid. The rest of the aldehyde is now precipitated by means of more sodium hydroxide solution, and comes down almost white. At the very end of the neutralization, particularly if the original product was quite yellow, the last 4 to 5 G of aldehyde should be precipitated separately, as they are inclined to be slightly colored. If too much alkali is added towards the end of the neutralization, a brown color appears, but the addition of a little hydrochloric acid will destroy this color. The main portion of the precipitate is filtered and dried. It weighs 95 to 100 g, m, p, 73 feet 0 inches. The succeeding runs yield 115 to 128 g of finished product, on account of the extra crude material obtained from the distillation and reprecipitation of the previous run. 2. Notes. The aldehyde that is obtained without reprecipitation gradually takes on a pinkish tinge on exposure to light. After the reprecipitation, however, this characteristic disappears. Thorough washing of the crude aldehyde is particularly desirable, as it removes a reddish impurity which tends to distill over and color the product lemon yellow, or sometimes even brownish yellow. When such a brownish product is obtained, it is quite necessary to make a second precipitation, as well as to observe the directions mentioned in the purification of the crude aldehyde, namely, to precipitate the first few grams and the last few grams of the aldehyde separately. The precaution of rejecting the first and last portions of the precipitate is unnecessary in the reprecipitation. In the reprecipitation of a deeply colored product, the portion of aldehyde at the end may be even purplish in color, and particular care must be taken to keep this separate. Vigorous mechanical stirring must be employed during the precipitation of the crude aldehyde, as otherwise large lumps are formed which make washing difficult. A previous investigator has mentioned that the crude product must be dried before distilling. This, however, is unnecessary. If the aldehyde is dried before distilling, it is possible to use a 500 cubic centimeters distilling flask instead of a 1L1. In purifying the aldehyde by dissolving in acid and reprecipitating, it is essential not to use stronger acid than that specified, 1:6, as stronger acid causes a deepening of the color of the solution. If the concentrated acid, which is to be diluted and used in this procedure, does not have a SPGR of 1.19, it will be necessary to add the equivalent amount of weaker acid in order to dissolve the p-dimethylaminobenzaldehyde. In purifying the aldehyde, sodium carbonate may be used in place of sodium hydroxide for precipitation, but it causes much foaming. When the apparatus for distilling, etc., is all set up, a run such as described above requires about 5 to 6 hours for completion. 3. Other methods of preparation. P-dimethylaminobenzaldehyde has been made by the condensation of chloral with dimethylaniline, and subsequent hydrolysis Wink-Witherfrown 1, by the hydrolysis of tetramethyldiaminobenzedrol with acetic acid Wink-Witherfrown 2, by the condensation of dimethylaniline, formaldehyde and M-sulfo-p-toluhydroxylamine followed by hydrolysis Wink-Witherfrown 3, by the electrolytic reduction of a mixture of sodium nitrobenzene sulfonate, dimethylaniline and formaldehyde, and subsequent hydrolysis Wink-Witherfrown 4, by the reduction of a mixture of dimethylaniline, formaldehyde and sodium nitrobenzene sulfonate with iron and hydrochloric acid, followed by hydrolysis Wink-Witherfrown 5, by the condensation of alloxan with dimethylaniline followed by hydrolysis Wink-Witherfrown 6, by the condensation of dimethylaniline, formaldehyde and sodium p-toluidine sulfonate in the presence of hydrochloric acid and potassium dichromate followed by hydrolysis. 7. The most satisfactory method, however, is the condensation of dimethylaniline, formaldehyde and nitrosodimethyl-aniline, followed by hydrolysis. 8. A method which was first described by E. Noel Ting and later perfected in detail by L. Baumann. 1 Br. 18, 1519, 1885, 19, 366, 1886, D. R. Page 61, 551, FRDL. 3. 109, 1892. 2. Br. 27, 3317, 1894. 3. D. R. P. 103,578, FRDL. 5. 101, 1899. 4. D. R. P. 105,103, FRDL. 5. 107, 1899. 5. D. R. P. 105,105, FRDL. 5. 109, 1899. 6. D. R. P. 108,086, FRDL. 5. 117, 1899. 7. D. R. P. 118,567, FRDL. 6. 133, 1901. 8. Br. 37, 858, 1904, J. Biology Chem. 41, 146, 1920. 6. Ethyl oxalate. Code 2H, 2 plus 2C2H50, Code 2C2H5, 2 plus 2H20. Prepared by H. T. Clark and W. Davis. Checked by Roger Adams and W. B. Burnett. 1. Procedure. In a 5L flask are placed 1 kilogram of crystallized, hydrated oxalic acid, 1.66 kilograms of 95% ethyl alcohol, and 1.33 kilograms of carbon tetrachloride. The flask is then fitted with a fractionating column, a meter long, to which is attached a condenser and an automatic separator so arranged that the lighter liquid flows off to a receiver, Figure 1. The heavier liquid flows through a tower of anhydrous potassium carbonate, and then returns to the reaction flask. The bottom of the tower is connected with a small separatory funnel through which any potassium carbonate solution, which flows from the solid in the tower, may be withdrawn from time to time. The mixture in the flask is slowly distilled. As soon as about 500 cubic centimeters of the lighter liquid has collected, it is placed in a fractionating apparatus and distilled, the material which boils up to 79 feet 0 inches being collected separately. This fraction, which consists principally of alcohol, with a little carbon tetrachloride and moisture, is dried with potassium carbonate and returned to the reaction mixture. The higher fractions are redistilled. The above process is continued until the distillate no longer separates into two phases, about 27 hours. The liquid in the flask is then distilled with the use of a column until the temperature of the vapor reaches 85 feet 0 inches. The residue is then distilled under reduced pressure, and the fraction which boils at 106-107/25 mm is collected. The yield is 920 to 960 g. Of a colorless liquid, 80 to 84% of the theoretical amount. 2. Notes. Water, ethyl alcohol, and carbon tetrachloride form a ternary mixture boiling at about 61 feet 0 inches. This vapor mixture, on condensation, separates into two phases. The heavier liquid consists of carbon tetrachloride and alcohol with only small amounts of water. The lighter liquid consists of approximately 65% alcohol, 25% water, and 10% carbon tetrachloride. By taking advantage of this fact, it is possible to conduct the esterification at a temperature so low that the ethyl hydrogen oxalate first formed does not decompose into ethyl formate and other products, as is the case when the customary methods of esterification are employed. The reaction may be carried out somewhat more expeditiously if the oxalic acid be dehydrated independently before it is mixed with the alcohol. Indeed, it is also possible to remove the bulk of the water from the alcohol itself by a similar method, before mixing it with the oxalic acid. However, since water is formed during the esterification, little is gained by this procedure. It is not absolutely necessary to remove the last traces of water from the alcohol carbon tetrachloride layer by means of potassium carbonate before returning it to the reaction mixture. This process is, however, so simple and requires so little attention that there is no doubt that it is of material aid in cutting down the time of operation. The advantages of using crystallized oxalic acid and commercial 95% alcohol, instead of the anhydrous reagents, are obvious. When technical oxalic acid is used, the yields are usually smaller by 5 to 10%. The apparatus shown in Figure 1 may be somewhat more simply constructed by using rubber connections in several places, thus eliminating a certain amount of glass blowing, and making a more flexible piece of apparatus. The sidearm of the separator may be made with 2 rubber connections, one above and one below the tube leading to the potassium carbonate tube. The long return tube to the flask may be constructed with a rubber joint very near the carbonate tube, and one near the flask. 3. Other methods of preparation. Ethyl oxalate has been prepared in poor yields by the following methods. By distilling a mixture of anhydrous oxalic acid and absolute alcohol with around 1. By heating a mixture of anhydrous oxalic acid and 97% alcohol under a reflux condenser and fractionating the resulting mixture with around 2. By distilling a mixture of anhydrous oxalic acid and absolute alcohol. The vapor of absolute alcohol being passed simultaneously into the mixture with around 3. By allowing a saturated solution of oxalic acid and alcohol to stand for a long time at 40-50 foot 0. 4. A good yield has been obtained by Anschutz. 5. By a method involving saturation of a mixture of crystallized oxalic acid and alcohol with hydrogen chloride, removal of the alcohol and water by distillation under reduced pressure, and repetition of the treatment with the alcohol and hydrogen chloride, the process being carried out several times. 1 Jars. 1861, 598. 2 J. Pracht. Chem. 234, 500, 1886. 3 Monich. 17, 614, 1896. 4 and 65, 350, 1848. 5 Br. 16, 24, 14, 1883. 7 Ethyl phenylacetate. C6H5CH2CN plus C2H5O plus H2SO4 plus H2O, C6H5CH2CO2C2H5 plus NH4SO4. Prepared by Roger Adams and A. F. Thal. Checked by Oliver Combe. 1. Procedure. In a 3L, round-bottom flask, fitted with an efficient reflux condenser, are mixed 750 g of 95% alcohol, 750 g of concentrated sulfuric acid and 450 g of benzyl cyanide. The mixture, which soon separates into 2 layers, is heated to boiling over a low flame for 6 to 7 hours, cooled and poured into 2L of water, and the upper layer is separated. This is washed with a little 10% sodium carbonate solution to remove small amounts of phenylacetic acid which may have been formed, and then distilled in vacuo. A small amount of water goes over first, and then a pure product boiling 132-138 foot 0/32 mm, 120-125 0/17-18 mm. The yield varies in general between 525 and 550 g. 83 to 87% of the theoretical amount. 2. Notes. The benzyl cyanide can be most conveniently prepared according to the directions in Preparation 3, page 9. The product which boils over a 5 feet 0 inches range should be used. In washing the layer of ethyl phenylacetate with sodium carbonate, it is sometimes advisable to add a certain amount of sodium chloride so that the ester will separate more readily. The product obtained is water clear and practically colorless. Although the product is collected over a 5 feet 0 inches range, most of the liquid is found to boil over a 1 foot 0 inches range, if distilled slowly without superheating. The boiling point of ethyl phenylacetate is near that of benzyl cyanide. However, a Sheldal analysis of the product shows that only a trace of nitrogen compounds is present. 3. Other methods of preparation. Ethyl phenylacetate may be prepared by the treatment of benzyl cyanide with alcohol and hydrochloric acid gas. 1. It is much more convenient in the laboratory, however, to use sulfuric acid in place of hydrochloric acid. In fact, the yields obtained are better than those recorded in the literature. This ester may also be made by the esterification of phenylacetic acid with hydrochloric acid and alcohol with a 2, or with alcohol and sulfuric acid with a 3. The following less important methods of preparation may be mentioned. The action of benzyl magnesium chloride upon ethyl chlorocarbonate 4, and the action of copper on a mixture of bromobenzene and ethyl chloroacetate at 180 Foot 5. 1 Br. 20, 592, 1887, and 296, 361, 1897. 2 Br. 2, 208, 1869. 3, and 296, 2, footnote, 1897, Comptroller Rend. 152, 1855, 1911. 4 Br. 36, 3088, 1903. 5 Br. 2, 738, 1869. 8. Glycerol A, G-dichlorohydrin. C3H5, O, 3 plus 2 HCl, CH2 Chalk 2 Cl plus 2 H2O. Prepared by J. B. Conant and O. R. Quayle. Checked by O. Com and A. O. Matthews. 1. Procedure. 1 kilo of 90% glycerol, SPGR 1.243, and 20 g of acetic acid are placed in a weighed 2L flask which is immersed in an oil bath heated to 100-110 Foot 0. The flask is fitted with a 2-hole stopper, which carries a long tube reaching to the bottom of the flask and a short exit tube. The former is connected to a hydrogen chloride generator, the latter to a catch bottle and some system for absorbing any excess of hydrogen chloride. A stream of dry hydrogen chloride is passed into the mixture. The absorption of gas is very rapid at the start, but gradually falls off towards the end of the reaction. The stream of hydrogen chloride should be regulated accordingly. The flask is removed from time to time and weighed. When the absorption of gas practically ceases, the increase in weight will be about 875 g, 25% more than the theoretical amount. The product is now cooled, placed in a 4L beaker, and treated with solid sodium carbonate until just alkaline to litmus. Water is added from time to facilitate the reaction with the sodium carbonate and to prevent the separation of salt. About 500 cubic centimeters are required. The mixture is transferred to a separatory funnel and the aqueous layer separated. The crude dichlorohydrin, which weighs 1250 g, is distilled in vacuo. The first fraction boiling below 68 Foot 0/14 mm weighs 225 g, and consists of water and some dichlorohydrin. The dichlorohydrin is collected between 68-75 0/14 mm, and weighs about 775 g. The water is separated from the first fraction, which is then redistilled and yields 100 g of dichlorohydrin. A still further amount of material, 40 to 45 g, may be obtained by extracting with benzene, the aqueous layer obtained in the neutralization process. This is, however, hardly profitable. The neutralization and distillation will require about 4 hours. The 875 g of dichlorohydrin thus obtained boils over a 7 feet 0 inches range. This is 70% of the theoretical amount. Redistillation yields 700 to 720 g, boiling 70-73 Foot 0/14 mm, 57% of the theoretical amount. 2. Notes. The most convenient hydrogen chloride generator is that described by Sweeney. 1. Concentrated hydrochloric acid is introduced into concentrated sulfuric acid, by means of a dropping funnel and a capillary tube leading to the bottom of the sulfuric acid container. It is convenient to use a 3L bottle for this container and a 1L funnel to contain the hydrochloric acid. The gas is dried by passing through a wash bottle containing concentrated sulfuric acid. An empty catch flask should be connected between the generator and the absorption flask in case any glycerol tends to suck back at the start of the reaction. About 6 kilograms of concentrated hydrochloric acid and 10 kilograms of concentrated sulfuric acid are required in one run. The generating flask will have to be recharged every 6 hours. it should be half filled with sulfuric acid. Aside from this, the apparatus needs no attention. The oil bath can be conveniently heated on an electric hot plate. The dichlorohydrin boiling over a 7 feet 0 inches range is sufficiently pure for most purposes. It contains very little, if any, isomeric dichlorohydrin, since on oxidation it gives dichloroacetone in good yields. 3. Other methods of preparation. The following methods of preparing dichlorohydrin are described in the literature. The action of gaseous hydrogen chloride on glycerol winkwithafrown 1b, the action of gaseous hydrogen chloride on glycerol mixed with an equal volume of acetic acid winkwithafrown 2, the action of hydrogen chloride gas on glycerol containing 1 to 2% of some organic acid, as acetic. As a catalyst winkwithafrown 3, the action of aqueous solution of hydrochloric acid on glycerol containing acetic acid as a catalyst winkwithafrown 4. The action of sulfur monochloride on glycerol. 5. The previous work, described in the literature, indicated that the best yields were obtained by the treatment of glycerol containing 1 to 2% of acetic acid as a catalyst by gaseous hydrogen chloride. Therefore, this method was employed. 1A J. M. Chem. SOC 39, 2187, 1917. 1B. And 88, 311, 1853, and Chim. Phys. 341, 297, 1854, 6, 22, 437, 1891, Bull. SOC Chim. 248, 237, 1887, Z. Physic. Chem. 92, 717, 1918, 93, 59, 1919, 94, 691, 1920, D. RP. 263,106, 272,337, FRDL. 11, 33, 1912. 2 and SBL. 1 2I8 1861, and Chim. Phys. 360 18 1860. 3D. R. P. 197,308, FRDL. 9 33 1908. 4D. R. P. 197,309, FRDL. 9 33 1903. 5 and 122 73 1862, 168 43 1873, BR. 5 354 1872, and Chim. Phys. 6 22 437 1891. 9. Glycerol amonochlorohydrin. C3H5, O, 3 plus HCl, CH2 Kchak 2O plus H2O. Prepared by J. B. Conant and O. R. Quayle. Checked by O. Com and A. O. Matthews. 1. Procedure. 500 grams of glycerol, 90%, and 10 g. of glacial acetic acid are mixed in a weighed 1L. flask, which is placed in an oil bath heated to 105-110 foot 0. A rapid stream of dry hydrogen chloride is introduced into the mixture. The flask is removed from the bath from time to time and reweighed. At the end of about 4 hours, the flask will have gained 190 g in weight. The reaction is then complete. The product is distilled under diminished pressure. Below 114 foot 0/14 mm, 220 to 250 g. Distill. This portion is mostly water. The monochlorohydrin is collected between 114-120 foot 0/14 mm. It weighs 360 g, which is 66% of the theoretical amount. About 20 g. More may be obtained by neutralizing the first fraction and separating the aqueous layer. 2. Notes. The same apparatus is employed as in the preparation of dichlorohydrin, preparation 8, page 29. The portion boiling 120-130 foot 0/14 mm only amounts to 15 to 30 g, showing that very little of the B compound is formed. This is further shown by the fact that the dichlorohydrin formed by continued action of hydrogen chloride under the same conditions contains very little, if any, A-B dichloride. 2 kg of concentrated sulfuric acid and 750 g of concentrated hydrochloric acid are sufficient to produce the necessary amount of hydrogen chloride. A light straw-colored final product is obtained in some cases. An alternative procedure which is slower and gives slightly lower yields, but does not require a hydrogen chloride generator, is as follows. 300 grams of glycerol, 600 cubic centimeters of hydrochloric acid, SPGR 1.19, and 15 g of glacial acetic acid are heated under a reflux condenser for 10 hours in a 2L flask. The boiling should be very gentle in the early stage of the reaction, as considerable hydrochloric acid vapor is evolved. As the reaction progresses, and the evolution of acid vapors diminishes, the mixture is more strongly heated. The reaction products are distilled under ordinary pressure until the temperature of the liquid has reached 140 feet 0 inches, thermometer bulb immersed in the liquid. The residual products are distilled under diminished pressure, and the following fractions obtained. 1. Up to 115 foot 0/11 mm. 2. 115-117 0/11 mm. 3. 117-170 0/11 mm. 1. Is mostly aqueous hydrochloric acid. 2. Is the monochlorohydrin. And 3. Is glycerol. The second portion is redistilled and the portion boiling at 115-118 foot 0/11 mm or 133-136 0/20 mm is collected. The yield is 190 to 205 g, 53 to 57% of the theoretical amount. 3. Other methods of preparation. The following methods of preparing monochlorohydrin are described in the literature. Action on glycerol of gaseous hydrogen chloride Winkwitherfrown 1. Action of gaseous hydrogen chloride on glycerol mixed with an equal volume of acetic acid Winkwitherfrown 2. Action of aqueous hydrochloric acid on glycerol. 3. Alone or with an organic acid, 1 to 2%, such as acetic. As a catalyst Winkwitherfrown 4. Gaseous hydrogen chloride with an organic acid, as acetic. As a catalyst Winkwitherfrown 1b. Gaseous hydrogen chloride with the ester of an organic or inorganic acid as a catalyst Winkwitherfrown 2b, the action of sulfur monochloride on glycerol. 3b. 1 and 88, 311, 1853, and Chim. Phys. 3, 41, 297, 1834, v. R. p. 254,709. 269,657, FRDL. 11, 31, 1912. 2 and Chim. Phys. 3, 60, 18, 1860. 3D. R. P. 180,668, FRDL. 8, 27, 1907, J. M. Chem. SOC 42, 2096, 1920. 4D. R. P. 197,309, FRDL. 934, 1908. 1BD. R. P. 197,308, FRDL. 933, 1908. 2BD. R. P. ANM. 23,510, 16,579, FRDL. 936, 1908. 3BD. R. P. 201,230, FRDL. 935, 1908. X-hydrazine sulfate. 2NH3 plus nickel, NH2NH2 plus H2O plus NaCl. Prepared by Roger Adams and B. K. Brown. Checked by J. B. Conant and W. L. Hanaway. 1. Procedure. A normal solution of sodium hypochlorite is prepared as follows. In a 5L round-bottom flask are placed 1800 g of sodium hydroxide solution, 300 g of sodium hydroxide to 1500 g of water, and 1500 g of ice. Chlorine gas is then passed into the solution until it has gained in weight approximately 213 g. During this addition, the solution must be kept thoroughly cooled with ice, in order that chlorates will not be formed. After all the chlorine has been passed in, it is necessary to be certain that the mixture is slightly alkaline, since any excess of free chlorine in the solution prevents the formation of hydrazine. In a 14-inch evaporating dish are placed 1,500 cubic centimeters of C.P. ammonia water, SPGR 0.90, 900 cubic centimeters of distilled water, 375 cubic centimeters of 10% gelatin solution, and 1,200 cubic centimeters of the normal sodium hypochlorite solution prepared as above. This mixture is heated as rapidly as possible and boiled down until 1/3 of the original volume is left. This solution is then cooled thoroughly with ice and filtered with suction, first through 2 layers of toweling and then through 1 thickness of ordinary filter paper over cloth, in order to remove finely divided solid impurities. The solution is then placed in a precipitating jar and cooled down thoroughly, 0 feet 0 inches, with ice and salt, 10 cubic centimeters of concentrated sulfuric acid for each 100 cubic centimeters of solution are gradually added with constant stirring. A precipitate of hydrazine sulfate, NH2NH2.H2SO4 forms. The mixture is allowed to stand in the cold for a few hours in order to complete the precipitation, and is then filtered by suction in the usual way and washed with cold alcohol. The yield varies from 53 g to 58 g per 1,500 cubic centimeters of ammonia water, 34 to 37% of the theoretical amount. The product is perfectly white and crystalline, and satisfactory for almost any purpose. If an absolutely pure product is desired, it must be recrystallized from water. For every 21 g of crude product, 100 g of boiling water are used. If the crude hydrazine is brown, it is advisable to use a little bone black. After the mixture has been filtered and cooled to 0 feet 0 inches, 19 g of pure white crystals are obtained. 2. Notes. In the preparation of the sodium hypochlorite solution, it is quite necessary that the mixture be kept cold and be alkaline to red litmus paper at the end of the reaction, if good yields of hydrazine are to be obtained. Since iron is an anticatalyzer, it is necessary, to use distilled water throughout the process. As a viscalizer, a substance such as starch, glycerol, glue, or gelatin may be used. The last, however, gives by far the most satisfactory results. In order to obtain a pure white hydrazine sulfate as the first precipitate, it is necessary to cool the hydrazine solution thoroughly and filter it twice before the sulfuric acid is added. Moreover, the sulfuric acid must be added slowly and with stirring. If these conditions are not followed, material containing brown particles results. The mother liquor obtained from the crystallized hydrazine sulfate contains a small amount of hydrazine. If 200 g of copper sulfate are dissolved in water and added to 10 L of the filtrates from the above processes, a light blue crystalline precipitate of the double salt of copper sulfate and hydrazine sulfate will be formed after 10 hours. This salt, when suspended in 10 times its weight of distilled water and treated with hydrogen sulfide, decomposes into copper sulfide and hydrazine sulfate. After the copper salt has been filtered off, the solution is concentrated until the hydrazine sulfate crystallizes. The yield of product is small, so that it is hardly advisable to undertake this recovery in the laboratory. It is possible for one man, simultaneously evaporating 6 dishes of the hydrazine mixture, to turn out from 20 to 25 rounds in 9 hours. The time for the evaporation of a solution, such as is mentioned in the experimental part, with a 4-flame Bunsen burner, is 2 to 3 hours. If the evaporation is carried out more slowly than this, the yield of product is distinctly diminished. 3. Other methods of preparation. Hydrazine salts have been prepared by the action of hypochlorites on ammonia, 1, or urea Winkwitherfrown 2, by the hydrolysis of salts of sulfohydrazimethylene disulfonic acid Winkwitherfrown 3, by the hydrolysis of triazoacetic acid Winkwitherfrown 4, by the reduction of diazoacetic ester wink with a frown 5. By the reduction of nitroguanidine followed by hydrolysis wink with a frown 6. By the reduction of the nitroso derivatives of hexamethylene tetramine wink with a frown 7. By the reduction of nitrates or nitrites with zinc in neutral solution wink with a frown 8. By the action of sodium bisulfite on hyponitrous acid followed by reduction wink with a frown 1b. By the reduction of K2SO3N2O2 wink with a frown 2b. By the action of ammonia on dichloriurea wink with a frown 3b. By the reduction of nitrosoperaldehyde wink with a frown 4b. By the action of copper sulfate on ammonia at high temperatures wink with a frown 5b. By the reduction of methylene disonitrosoamine wink with a frown 6b. By the hydrolysis of the addition product of diazoacetic ester and fumaric or cinnamic esters, 7b. 1d. R. P. 192,783, Chem. Center. 1908 I. 427, Chem. CTG. 31, 926, 1907, D. R. P. 198,307, Chem. Center. 1908 I. 1957, Ing. Pat. 22,957, C. A. 2 1999, 1908, U. S. Pat. 910,858, C. A. 3 1065, 1909, French Pat. 382,357, C. A. 3 2358, 1909, Br. 40, 4588, 1907, Laboratory Manual of Inorganic Preparations, by A. B. Lamb, Harvard University, Cambridge, Massachusetts. 2 J. Russ. Phys. Chem. SOC 37, 1, 1905, Chem. Center. 1905, I. 1227, D. R. P. 164,755, FRDL. 853, 1905, French Pat. 329,430, J. SOC Chem. IND 22, 1063, 1903, Chem. Center. 1905, I. 1227. 3D. R. P. 79,885, FRDL. 4, 26, 1895, BR. 28, 2381, 1895. 4 BR. 20, 1632, 1887, Chem. News 55, 288, 1887, D. R. P. 47,600, FRDL. 2, 554, 1889, J. Pract. Chem. 2, 39, 27, 1889. 5 BR. 27, 775, 1894, 28, 1848, 1895, D. R. P. 58,751, FRDL. 3, 16, 1891, D. R. P. 87,131, FRDL. 4, 28, 1896. 6, and 270, 31, 1892, D. R. P. 59,241, FRDL. 3, 16, 1891, N. Pat. 6,786, J. SOC Chem. IND 11, 370, 1892. 7 D. R. P. 80,466, FRDL. 4, 27, 1895, and 288, 232, 1895. 8 Pat. 11, 216, J. SOC Chem. IND 14, 595, 1895. 1 B BR. 33, 2115, 1900, and 288, 301, 1895. 2 B BR. 27, 3498, 1894. 3BJ, Chem. SOC 95, 235, 1909, Chem. News 98, 166, 1908. 4BBR. 23, 752, 1890. 5B Chem. News 66, 223, 1892. 6BBR. 27, 3292, 1894. 7BBR. 21, 2637, 1888. 11 Acetylene. 3CH3 COC3 plus, H2SO4, C6H3, CH3, 3 plus 3 H2O. Prepared by Roger Adams and R. W. Hufford. Checked by H. T. Clark and W. W. Hartman. 1. Procedure. In a 12L, round-bottom flask, arranged so that the contents can be mechanically stirred, are placed 4,600 g, 5,750 cubic centimeters, of technical acetone. The flask is then well cooled with an ice and salt mixture, until the temperature of the acetone is between 0 feet 0 inches and 5 feet 0 inches. Stirring is started, and 4,160 cubic centimeters of commercial concentrated sulfuric acid is run in at such a rate that the temperature of the mixture never rises above about 10 feet 0 inches. This addition is accomplished in about 5 to 10 hours. The stirring is continued for 3 to 4 hours longer, while the flask still remains immersed in the original freezing mixture to which no further amount of ice is added. The mixture is then allowed to stand at room temperature for 18 to 24 hours. A 5L round-bottom flask is fitted with a rubber stopper or a cork stopper coated with pitch, carrying 2 glass tubes, one of which, for the entrance of steam, reaches to the bottom of the flask, while the other extends into the open end of a condenser set for downward distillation. The stopper should be wired into the flask. The glass delivery tube into the condenser should not be less than a 12 mm bore, and the condenser should consist of 2 120 cm water-cooled condensers attached end to end. To the end of the condensing system, an adapter is attached, the small end of which is at least 8 mm in bore and is fitted tightly into a stopper in a 2L suction flask. To the side arm of the suction flask is attached a tube leading to an exhaust fan, in order to carry away the gases which are evolved during the subsequent distillation. In the 5L flask are placed about 2L of the sulfuric acid-acetone reaction mixture, and the flask is then heated with a free flame and shaken occasionally. A reaction starts at the end of about 15 or 20 minutes, as shown by the evolution of gas, chiefly sulfur dioxide, and is allowed to run for about 3 minutes. At the end of this time, a current of steam is passed in and continued for about 3 minutes. During this period a large proportion of the acetylene distills and should be kept separate from the subsequent distillate. The steam distillation is continued at such a rate that about 800 cubic centimeters distills in 25 to 30 minutes and is collected as a second distillate. At the end of this time, the distillation is stopped, the water poured off from the distilling flask and the tarry material emptied out while hot into waste jars. The total amount of original reaction mixture requires 5 distillations similar to the one just described. The first distillates from each of the 5 distillations are mixed, and the layer of acetylene is separated from the water. This is shaken with sodium hydroxide solution until no more odor of sulfur dioxide is noticeable, then washed twice with water and distilled. The first portion of the distillate consists of a small amount of water and acetylene, and is added to the combined second distillates. The fraction which distills up to 210 feet 0 inches is saved. The second distillates are combined, washed in the same way as the first, and then distilled. The fraction which distills up to 210 feet 0 inches is combined with the corresponding fraction from the first distillates. These combined fractions, which boil up to 210 feet 0 inches, and 15 g of sodium are placed in a 2L distilling flask, the sidearm of which is closed with a rubber tube and pinch cock and which is fitted with a reflux condenser. The mixture is heated just below the boiling point for about 3 hours, during which time the impurities are attacked by the molten sodium, and a gelatinous, reddish mass forms. The reflux condenser is now removed and one set for downward distillation is attached to the sidearm. The mixture is distilled and about 2/3 of the liquid removed in this way. The residue is cooled, the liquid poured off from solid material and distilled up to 210 feet 0 inches. The distillates from the sodium treatment are now fractionated with a good column, at least 30 centimeters long, and the portion which boils at 163-167 foot 0 is collected. The yield of this fraction varies in different runs from 430 to 470 g, 13 to 15% of the theoretical amount, but very often will be as high as 500 g, and has reached, in certain experiments, 600 g. An alternative method for the purification of the crude material has been employed by Clark and Hartmann, and yields a slightly higher grade product than the sodium method. It is as follows. The combined distillates are treated with an equal volume of concentrated sulfuric acid and the solution warmed on a water bath for an hour, under a reflux condenser, with occasional shaking or, better, with mechanical stirring. Upon cooling, macetylene sulfonic acid crystallizes and the unsulfonated material remains as an oil on the surface. The mixture is filtered through flannel or a filtrose plate, and the crystals are washed with 60 to 70% sulfuric acid. The oily layer is again warmed with sulfuric acid, as before. The acid and oily filtrates from the two sulfuric acid treatments are steam distilled, and the distillate combined with the next batch of material. The crystals are mixed with 2L of 15% hydrochloric acid and heated under a reflux condenser for 2 to 3 hours. The reaction mixture is now steam distilled, the macetylene separated, dried over calcium chloride and fractionated. The portion which boils at 163-167 foot 0 is collected. 2. Notes. The cooling of the reaction flask must be very efficient, a 10 to 15 centimeters blanket of a thorough mixture of ice and salt being used. If this precaution is not employed, the time for the addition of the sulfuric acid is greatly increased, provided the temperature of the reaction mixture is still kept within the limits mentioned. If a cork is used for the steam distillation of the reaction mixture of acetone and sulfuric acid, it should be coated well with pitch and wired into the flask. This is necessary because the vapors of the reaction mixture attack an ordinary cork very badly, and soften it so much that it is necessary to rewire it to prevent it from slipping out. A rubber stopper is satisfactory and may be used in several runs. The evolution of gas is so vigorous that it is not possible to distill more than 2L of the original reaction mixture at one time in the apparatus described. The connections on the apparatus, in which the macetylene is obtained from the crude reaction mixture, should be tight, since the fumes evolved during the heating are very irritating. The product which distills during the initial heating and the 3 minutes of steam distillation is mainly satisfactory material. The rest of the steam distillation yields only a small amount of pure product. The two portions of the distillate are, therefore, kept separate, since the second distillate always contains a considerable amount of high boiling product which tends to cause emulsification of the alkali in the purification. No recovery of acetone is made. The mechanism of the reaction is undoubtedly as follows. When the sulfuric acid and acetone are in contact for long periods of time, several molecules of the acetone condense to form aldol condensation products. These do not break down into macetylene until the temperature is raised in the second part of the experiment. While the original reaction mixture is standing, the temperature gradually rises to 40 feet 0 inches or 50 feet 0 inches in the course of 6 to 10 hours, and then gradually cools off again. It is probable that at the end of this time, when the flask has cooled again, the reaction mixture could be distilled with nearly as good a yield as is obtained after standing 18 to 24 hours. The wide variation in yields which are mentioned in the experimental part is probably due to a slight change in the grade of the chemicals which are used in this preparation. 3. Other methods of preparation. The cheapest and most convenient method by which macetylene may be prepared is by the action of a dehydrating agent upon acetone. The agent most commonly used is sulfuric acid. 1. It has been shown also that phosphoric acid will convert acetone to macetylene. 2. A number of other methods have also been used for the preparation of macetylene. The action of sulfuric acid on methyl acetylene wink with a frown 3. The action of sulfuric acid on mesodyl oxide and phorone wink with a frown 4. The action of aluminium, British chloride on methyl chloride and benzene wink with a frown 5. The action of mineral acids upon mesitol or benzoyl mesitylene wink with a frown 6. The action of phosphoric acid upon diacetylmesitylene wink with a frown 7. The treatment of methylene 3-dimethyl 1,5-cyclohexene 1 with bromine and then with alcoholic potash. 8. 1 and 141, 131, 1867, 147, 43, 1868, 278, 210, 1893, Bud. SOC Chim. 240, 267, 1883, J. Pract. Chem. 1, 15, 129, 1838, M. Chem. J. 15, 256, 1893, 20, 807, 1898. 2. J. Chem. SOC 99, 1251, 1911. 3. Br. 817, 1875. 4. Br. 7, 1169, 1874, 10, 858, 1877. 5. Br. 12, 329, 1879, and Chim. Phys. 6, 1, 461, 1884. 6. Br. 32, 1910, 1899. 7. Br. 32, 1563, 1899. 8. Br. 43, 3093, 1910. 12. Methyl red. O. Ho2cc6H greater than 4SNH2 plus NO2 plus HCl. O. Ho2cc6H4N2Cl plus H2O. O. Ho2cc6H4N2Cl plus C6H5N, CH3, 2, O. Ho2cc6H4N equals NC6H4N, CH3, 2 plus HCl. Prepared by H. T. Clark and W. R. Kerner. Checked by Roger Adams and J. B. Davis. 1. Procedure. Technical anthranilic acid, generally about 95% pure, 685 g, is dissolved in 1.5 L of water and 500 cubic centimeters of concentrated hydrochloric acid, SPGR 1.17, by heating. The insoluble dark impurity present in small amounts is filtered off, and the filtrate is transferred to a 10L crock and chilled with stirring. It is then mixed with a mush of 2.5 kilograms of ice and 750 cubic centimeters of concentrated hydrochloric acid. The crock is cooled externally with ice, and the contents stirred continuously. When the temperature reaches about 3 feet 0 inches, a filtered solution of 360 g of sodium nitrite and 700 cubic centimeters of water is dropped in slowly through a long capillary tube reaching below the surface of the liquid until a faint but permanent reaction to starch potassium iodide paper is obtained. The temperature is kept between 3 feet 0 inches and 5 feet 0 inches. This operation requires all but about 30 cubic centimeters of the nitrite solution and occupies 1.5 to 2 hours. To the solution of the diazonium salt are now added 848 g of dimethylanilin. This may be done rapidly, as the temperature does not rise appreciably. Stirring is continued for 1 hour, the temperature being kept at 5 feet 0 inches. 500 cc of a filtered solution of 680 g of crystallized sodium acetate diluted to 1,200 cubic centimeters are then added, and the stirring continued for 4 hours. If a foamy solid rises to the surface during this time and refuses to become incorporated by the stirrer, a few drops of ethyl acetate may be added to reduce the foam. The mixture is allowed to stand overnight in an ice bath which is well insulated by several thicknesses of burlap. The temperature must be kept below 7 feet 0 inches to get a good yield of product. The remainder of the sodium acetate solution is then added with stirring, and after the mixture has been stirred for an additional period of 1 to 3 hours, the temperature is allowed to rise slowly to 20-25°C in the course of 24 hours. Just enough sodium hydroxide solution is then added, with stirring, to cause the mixture to have a distinct odor of dimethylanilin, about 240 cubic centimeters of a 40% solution are generally required, and the mixture is allowed to stand for 48 hours or longer at room temperature, 20-25°C. The solid is then filtered off, washed first with water, then with 400 cubic centimeters of 10% acetic acid to remove the dimethylanilin, and finally with distilled water. The last filtrate is generally pale pink. The solid is sucked as dry as possible, spread out on a tray in order to allow most of the water to evaporate, 15 to 20 hours, and then suspended in 4L of methyl alcohol in a 12L flask. This mixture is stirred on the steam bath under a reflux condenser for 1 to 2 hours, allowed to cool slowly, and then chilled in an ice bath and filtered. The solid product is washed with a second 4L of cold methyl alcohol. After being dried in air, the product varies in weight from 820 to 870 g. The product is extracted with boiling toluene in the following manner: 150 g are placed in a fluted filter paper of 29 centimeters diameter in a 25 centimeter glass funnel which passes through the cork of a 2L flat-bottom conical flask containing 1,250 cubic centimeters of toluene, figure 2. The flask is heated on an electric stove, and a 12L round-bottom flask is placed on the funnel to act as a condenser, cold water being run through the flask. The toluene is boiled until the condensed liquid runs through almost colorless. This requires from 4 to 10 hours. The heating is then discontinued, and, as soon as the liquid ceases to boil, the flask is removed to a bath containing water at 90-100°C. The level of the water should be slightly above the level of the liquid in the flask. This arrangement permits the temperature to fall slowly so that large crystals are obtained. In the meantime, a second conical flask containing 1,250 cubic centimeters of toluene is attached to the funnel, and a new charge of 150 g of crude methyl red is placed in the paper. When extraction is complete, it is found that a certain amount of black amorphous insoluble matter remains on the filter. This is discarded. The crystals of methyl red are filtered off and washed with a little toluene. The weight of pure material is 755 to 805 g. The mother liquors are concentrated to 1/4 of their volume, and the crystals which separate on cooling are recrystallized from fresh toluene. The recovered toluene can, of course, be employed again. The total yield of pure methyl red is 790, 840 g. It melts at 181-182°C. The watery mother liquors from the crude methyl red are rendered alkaline with sodium hydroxide and distilled until no more dimethylanilin passes over. In this way 250 to 400 g of moist dimethylanilin are recovered. 2. Notes. The amount of hydrochloric acid indicated must not be reduced, otherwise diazoamino compounds are formed. It is essential to keep the temperature low while unreacted diazobenzoic acid remains in solution, in order to avoid decomposition. If this precaution is not taken, the yields are considerably diminished through the formation of tarry byproducts. The use of a capillary tube for the addition of sodium nitrite prevents loss of nitrous acid by local reaction at the surface of the acid solution. The tube should not be tightly connected to the dropping funnel, but should be so arranged that air is sucked through with every drop. In this way, the entrance of the acid liquor into the capillary is prevented. The formation of the azo compound takes place slowly on the addition of the dimethylanilin, but the speed of the reaction is greatly increased when the hydrogen ion concentration is lowered by the addition of the sodium acetate. It is nevertheless necessary to allow the reaction mixture to stand a long time. If the product be filtered off after only 24 hours, a further quantity of dye will separate from the filtrate on standing. The hydrochloride of methyl red is only sparingly soluble in cold water, and is apt to separate in blue needles if the acidity is not sufficiently reduced. The alcoholic filtrate, obtained on digesting and washing the crude methyl red, contains a more soluble red byproduct which gives a brownish-yellow solution in alkali. The methyl alcohol may be recovered with very little loss by distillation. It is, however, impracticable to attempt to recover any methyl red from the residue, owing to the tarry nature of the byproduct. The proportion of this byproduct is greatly increased if the temperature of the mixture is allowed to rise too soon after the addition of the sodium acetate. Methyl red is described as crystallizing in needles from glacial acetic acid. On recrystallization from toluene, it separates in plates. When the methyl red is crystallized from toluene, it sometimes separates in the form of bright red lumps, probably on account of too rapid crystallization. Under these conditions, it is advisable to crystallize again, using a somewhat larger amount of toluene. It is advisable to titrate the crude anthranilic acid with standard alkali and phenolphthalein before starting the experiment. In checking these directions, an 80% anthranilic acid was used. It gave a correspondingly lower yield of methyl red, 650 to 700 G. The yield of methyl red is about 65 to 70% based on the dimethylaniline actually used up, but only 58 to 63% based on the anthranilic acid actually present in the technical anthranilic acid employed. 3. Other methods of preparation. Methyl red was first prepared, 1. By diazotization of anthranilic acid in alcoholic solution, the product being allowed to react with dimethylaniline in the same solvent. It has been stated, 2, that this process does not work satisfactorily and yields a different product, of brownish red color. The preparation of methyl red in aqueous solution has been described by 2 workers, one of whom, 3, gives but few details and claims a nearly quantitative yield. The other, 4, gives fuller details and states the yield to be 43.1% of the theory. The recrystallization of methyl red from toluene is stated, 5, to yield a product melting at 183 feet 0 inches. 1 Br. 41, 3905. 1908. 2 Chem. Center. 1910 1, 960, 1910, 11, 1561. 3 J. Chem. SOC 97, 2485, 1910. 4 C. A. 14, 3406, 1920. 5 J. Chem. SOC 99, 1334, 1911. 13. P-nitrobenzoic acid. P. No 2C6H4CH3S plus 3O, Na 2Cr2O7 plus H2SO4, P. No 2C6H4Co2H plus 3H2O. Prepared by O. Com and A. O. Matthews. Checked by H. T. Clark and W. W. Hartman. 1. Procedure. In a 5L round-bottom flask, fitted with a mechanical stirrer, are placed 680 G of sodium dichromate, 1,500 cubic centimeters of water, and 230 G of p-nitrotoluene. Stirring is started, and 1,700 G of concentrated sulfuric acid are allowed to flow in during about 30 minutes. The heat of dilution of the sulfuric acid will cause the nitrotoluene to melt, and rapid oxidation will soon take place. The last half of the sulfuric acid must be added gradually, in order to prevent too violent a reaction. Since a small amount of nitrotoluene is volatilized, it is advisable to carry on this work under a hood. After the sulfuric acid has been added and the spontaneous heating of the reaction mixture has subsided, the mixture is heated to gentle boiling for about half an hour. After the reaction mixture has cooled, 2L of water are added, the cooled solution is filtered through a cloth filter, and the product washed with about 1L of water. In order to remove the chromium salts as completely as possible, the crude nitrobenzoic acid is warmed on the water bath and agitated with 1L of dilute, 5% sulfuric acid solution. After cooling, the product is again filtered. It is then dissolved in 5% sodium hydroxide solution, filtered from any chromium hydroxide remaining, and also from unchanged nitrotoluene. The filtrate, which should be light yellow or greenish in color, is acidified with dilute sulfuric acid, with stirring. It is usually preferable to run the alkaline solution into the dilute sulfuric acid, rather than to use the reverse procedure, for the precipitation of the nitro acid. The precipitated product is filtered with suction, washed thoroughly, and dried. The product should possess only a light lemon color. The yield should be 230 to 240 g, 80 to 85% of the theoretical amount. For a product of special purity, crystallization from benzene is advisable. For most purposes, however, the nitrobenzoic acid may be used without crystallization, since its melting point is found to be within 2 feet 0 inches of the correct value of 238 feet 0 inches. 2. Notes. The above procedure differs from that recorded in the literature, mainly in the use of a fairly large excess of sulfuric acid. This shortens the reaction time from 40 hours to about 1 hour, which is especially convenient in the preparation of the acid on a laboratory scale. Because of the use of this large excess of sulfuric acid, the reaction is apt to be rather violent if the directions given are not carefully followed. The oxidation should be carried out under a hood. Small amounts of nitrotoluene are lost by volatilization, but this loss is not serious, as can be seen from the yield of product obtained. 10 or 20 g of unchanged nitrotoluene can be recovered from the reaction mixture by steam distillation, but the value of the byproduct would not pay for the time spent in recovery. The washing of the crude reaction product with dilute sulfuric acid is advisable, if good material is to be obtained. If an efficient centrifuge is available for use at this stage of the operation, this separate washing may prove to be less essential. When a sparingly soluble organic acid is precipitated from fairly concentrated solution, the precipitate is liable to carry down with it some of the salt of the organic acid. Addition of the salt solution to the mineral acid, with stirring, avoids this difficulty. 3. Other methods of preparation. The nitration of benzoic acid produces only very small yields of the p-nitro product. 1. The only practical method for the preparation consists in the oxidation of p-nitrotoluene, although for this purpose various oxidizing agents are used. In addition to nitrotoluene, p-nitrobenzyl alcohol, p-nitrocinamic acid and similar compounds may be oxidized, but their cost is prohibitive in comparison with that of the cheaper nitrohydrocarbon. P-nitrotoluene may be oxidized by means of strong nitric acid, 2. Chromic acid mixture, 3. Or permanganates. 4. Electrolytic oxidation, 5. Has also been proposed. The procedure given above involves the use of chromic acid mixture, but, owing to a change in the concentration of sulfuric acid, the time of reaction is greatly shortened and the preparation is thus considerably improved. 1 Br. 8 528, 536, 1875. 2. And 127, 137, 1863, 128, 257, 1863. 3. And 139, 335, 1866. 4 J. M. Chem. SOC 41, 1575, 1919. 5. R. Page 117, 129, FRDL. 6. 112. 14 p-nitrobenzyl cyanide. C6H5CH2CN plus NO3, P, NO2C6H4CH2CN plus H2O. Prepared by G. R. Robertson. Checked by Roger Adams and H. O. Calvary. 1. Procedure. In a 2L, round-bottom flask, fitted with a stopper holding a dropping funnel and a mechanical stirrer, is placed a mixture of 275 cubic centimeters of concentrated nitric acid, SPGR 1.42, and 275 cubic centimeters of concentrated sulfuric acid, SPGR 1.84. This is cooled to 10 feet 0 inches in a freezing mixture, and 100 g of benzyl cyanide, free from alcohol and water, are run in slowly, at such a rate that the temperature remains at about 10 feet 0 inches and does not exceed 20 feet 0 inches. After all the benzyl cyanide has been added, about 1 hour, the ice bath is removed, the mixture is stirred for an hour and then poured on to 1200 g, of crushed ice. A pasty mass slowly separates. More than half of this mass is p-nitrobenzyl cyanide, the other constituents being O-nitrobenzyl cyanide, and a variable amount of an oil which resists hydrolysis. Apparently no dinitro compounds are formed. The mass is filtered on a porcelain funnel with suction, pressed well to remove as much oil as possible, and dissolved in 500 cubic centimeters of boiling alcohol, 95%. On cooling, p-nitrobenzyl cyanide crystallizes. The mother liquor, on distillation, gives an impure alcohol which can be used for the next run. Recrystallization from 550 cubic centimeters of 80% alcohol, SPGR 0.86 to 0.87, yields 70 to 75 G, 50 to 54% of a product which melts at 115-116 foot 0. This product is satisfactory for most purposes, and incidentally for the preparation of p-nitrophenylacetic acid. Occasionally it must be free even from traces of the ortho compound, and in this case should be crystallized again from 80% alcohol. It then melts at 116-117 foot 0. 2. Notes. Fuming nitric acid may be used in nitrating benzyl cyanide, but the method here described is cheaper. The yield of 70 G is obtained from benzyl cyanide, which boils over a 5 feet 0 inches range prepared as described in Preparation 3, page 9. Very pure benzyl cyanide will give a slightly higher yield, while commercial grades may give only 50 G of p-nitrobenzyl cyanide and much oil. The reaction has been also carried out with 500 G of benzyl cyanide. Under these conditions a 5L flask was used, and it required 2.5 hours to add the benzyl cyanide. The yield of product was 325 to 370 G. 3. Other methods of preparation. Nitrobenzyl cyanide has hitherto been prepared by the action of fuming nitric acid, 1, on benzyl cyanide. 1 Br. 17, 505, 1884, 33, 170, 1900, J. Biology Chem. 39, 585, 1919, J. M. Chem. SOC 43, 180, 1921. 15. P-nitrophenylacetic acid. P. No 2C6H4CN plus H2SO4 plus 2H2O. P. No 2C6H4CH2 Co2H plus NH4SO4. Prepared by G. R. Robertson. Checked by Roger Adams and H. O. Calvary. 1. Procedure. In a 1L round bottom flask are placed 100 G of p-nitrobenzyl cyanide, a solution of 300 cubic centimeters of concentrated sulfuric acid, SPGR 1.84, in 280 cubic centimeters of water is prepared, and 2/3 of this solution is poured onto the p-nitrobenzyl cyanide. The mixture is shaken well, until the solid is all moistened with the acid. Any solid material sticking to the walls of the vessel is now washed down into the liquid with the remainder of the acid. The flask is attached to a reflux condenser, then set, without shaking, over a 10-centimeter hole in a large sheet of asbestos board which rests on a tripod, and heated until the mixture boils. The boiling is continued for 15 minutes. The reaction mixture, which becomes rather dark, is diluted with an equal volume of cold water and cooled to 0 feet 0 inches or below. The solution is filtered, the precipitate is washed several times with ice water, and then dissolved in 1600 cc of boiling water. A few grams of animal charcoal are added in dissolving the precipitate, if the technical p-nitrobenzyl cyanide has been used. This solution is filtered as rapidly as possible through a large folded filter, preferably with a steam funnel. In spite of all precautions, however, some solid usually separates on the filter. This must be redissolved in a minimum quantity of boiling water, and this solution then filtered into the main solution. The p-nitrophenylacetic acid separates in long, pale yellow needles, which melt at 151-152 foot 0. The yield is 103 to 106 G, 90 to 3% of the theoretical amount. 2. Notes. If the flask is not protected with an asbestos board or the equivalent, decomposition occurs where the substance is superheated on the side walls of the flask. If crystals of the cyanide are allowed to remain on the upper walls of the flask, they are not easily washed down and so are not hydrolyzed. The solubility curve of p-nitrophenylacetic acid is very steep at temperatures near 100 feet 0 inches, so that the filtering of the boiling solution should be rapid. If a good grade of cyanide be used, it is not necessary to add bone black in order to obtain the acid in a pure state. In making experiments with 500 g of p-nitrobenzyl cyanide, it was found that the time for hydrolysis was about the same as when smaller amounts were used. 3. Other methods of preparation. P-nitrophenylacetic acid has been formed by the nitration of phenylacetic acid (1), by the hydrolysis of its ester, 2, or its amide, 3, and by the hydrolysis of its nitrile with hydrochloric acid, 4. 1 Br. 42, 3596, 1909. 2 Br. 12, 1765, 1879. 3 Br. 14, 2342, 1881. 4 Br. 15, 834, 1882. 16. Nitrosobenaphtol. C10H7OB plus NO2, C10H6O NO1, 2 plus H2O. Prepared by C. S. Marvel and P. K. Porter. Checked by H. T. Clark and W. W. Hartman. 1. Procedure. In a 12L, round-bottomed flask fitted with a mechanical stirrer are placed 500 g of technical B-naphthol dissolved in a warm solution of 140 g of sodium hydroxide and 6L of water. The solution is cooled to 0 feet 0 inches in an ice and salt bath, and 250 g of powdered technical sodium nitrite is added. Stirring is started and 1100 g of sulfuric acid, SPGR 1.32, are added from a dropping funnel, at such a rate that the whole is added in 1 to 1.5 hours, the temperature being kept at 0 feet 0 inches. During the reaction, crushed ice is added from time to maintain the temperature at 0 feet 0 inches, about 1 kilogram. Is usually used. After all of the sulfuric acid has been added, the solution should react acid to Congo paper. The mixture is stirred 1 hour longer at the low temperature, and then the nitrosobenaphtol, which has gradually separated out during the reaction, is filtered with suction and washed thoroughly with water. The product is at first light yellow in color, but after 3 to 4 days it gradually changes to a dark brown. The moisture content seems to have some effect on the color. After the product has been air-dried for about 4 days, the yield is about 665 g. It melts at 97 feet 0 inches. A sample of this partially dried product, on drying in vacuo over sulfuric acid for 20 hours, loses about 10% of its weight, and the melting point is 106 feet 0 inches. By longer drying under ordinary conditions, the melting point of 106 feet 0 inches is reached. The total yield of dry product is about 595 g, 99% of the theoretical amount. This product is satisfactory for all purposes. It may be obtained in a crystalline condition, however, by recrystallizing from hot ligroin, SPGR 0.71 to 0.72. About 2 g of nitrosobenaphtol will dissolve in 15 cubic centimeters of boiling ligroin. The product is not very soluble in cold ligroin, so that nearly all is recovered. 2. Notes. It is very necessary to keep the temperature near 0 feet 0 inches while adding the sulfuric acid, or a tarry product will be obtained. Vigorous stirring and the addition of the sulfuric acid at the proper rate are essential for a good product. A large vessel is needed for the reaction, as the nitrosobenaphtol separates in a finely divided condition and there is some tendency to foam. The final air-dried product is pure except for its moisture content, as is shown by the fact that on drying in vacuo it has a very good melting point. A sample of Kalbaum's nitrosobenaphtol melted at 101, 105. 3. Other methods of preparation. Nitrosobenaphthol has been made by the action of hydroxylamine hydrochloride on benaphthocquinolchloramide winkwithafrown 1, by the action of sulfuric acid upon a solution of potassium or sodium nitrite and the sodium salt of benaphthol winkwithafrown 2, by the action of sodium nitrite upon an alcoholic solution of zinc chloride and benaphthol winkwithafrown 3, by the action of sodium nitrite upon benaphthol suspended in zinc sulfate solution winkwithafrown 4, by the action of nitrous acid on benaphthol methane winkwithafrown 5, and by the action of nitrosyl sulfate upon the sodium salt of benaphthol. 6. 1 Br. 27, 241, 1894. 2 Br. 8, 1026, 1875, 27, 3076, 1894, J. Chem. SOC 45, 295, 1884. 3 Br. 18, 705, 1885. 4 D. R. P. 25469, FRDL. 1, 335, 1883. 5 Br. 33, 806, 1900. 6 J. Chem. SOC 32, 47, 1877, and 189, 146, 1877. 17 Phenylacetic acid. C6H5CH2CN plus 2H2O plus H2SO4, C6H5CH2CO2H plus NH4SO4. Prepared by Roger Adams and A. F. Thal. Checked by O. Com and A. O. Matthews. 1. Procedure. In a 5L, round-bottom flask, fitted with a mechanical stirrer and reflux condenser, are mixed 1,150 cubic centimeters of water, 840 cubic centimeters of commercial sulfuric acid, and 700 g of benzyl cyanide. Preparation 3, page 9. The mixture is heated under a reflux condenser and stirred for 3 hours, cooled slightly, and then poured into 2L of cold water. The mixture should be stirred so that a solid cake is not formed. The phenylacetic acid is then filtered off. This crude material should be melted under water and washed by decantation several times with hot water. These washings, on cooling, deposit a small amount of phenylacetic acid which is filtered off and added to the main portion of material. The last of the hot water is poured off from the material while it is still molten, and it is then transferred to a 2L Claisen distilling flask and distilled in vacuo. A small amount of water comes over first and is rejected, about 20 cubic centimeters, containing an appreciable amount of benzyl cyanide, then distills. This fraction is used in the next run. The distillate boiling 176-189 foot 0/50 mm is collected separately and solidifies on standing. It is practically pure phenylacetic acid, P. 76-76.5 foot 0. It amounts to 630 g, 77.5% of the theoretical amount. As the fraction which is returned to the second run of material contains a considerable portion of phenylacetic acid, the yield actually amounts to at least 80%. For the preparation of small quantities of phenylacetic acid, it is convenient to use the modified method given in the notes. 2. Notes. The standard directions for the preparation of phenylacetic acid specify that the benzyl cyanide is to be treated with dilute sulfuric acid prepared by adding 3 volumes of sulfuric acid to 2 volumes of water. Their action, however, goes so vigorously that it is always necessary to have a trap for collecting the benzyl cyanide which is blown out of the apparatus. The use of the more dilute acid, as described in the above directions, is more satisfactory. The phenylacetic acid may also be made by boiling under a reflux condenser for 8 to 15 hours, without a stirrer, but this method is not nearly so satisfactory as that described in the procedure. When only small quantities of the acid are required, the following modified procedure is of value. 100 grams of benzyl cyanide are added to a mixture containing 100 cubic centimeters of water, 100 cubic centimeters of concentrated sulfuric acid, and 100 cubic centimeters of glacial acetic acid. After this has been heated for 45 minutes under a reflux condenser, the hydrolysis is practically complete. The reaction mixture is then poured into water, and the phenylacetic acid isolated in the usual manner. The odor of phenylacetic acid is disagreeable and persistent. 3. Other methods of preparation. The standard method of preparation of phenylacetic acid is by the hydrolysis of benzyl cyanide with either alkali, 1A, or acid, 2A. The acid hydrolysis runs by far the more smoothly, and so was the only one studied. There are numerous other ways in which phenylacetic acid has been formed, but none of them is of practical importance for its preparation. These methods include the following: the action of water on phenylketene Winkwitherfrown 3A, the hydrolysis and subsequent oxidation of the product between benzaldehyde and hippuric acid Winkwitherfrown 1, the reduction of mandelic acid Winkwitherfrown 2, the reduction of benzoylformic acid with hydriodic acid and phosphorus Winkwitherfrown 3, the hydrolysis of benzyl glyoxylidone Winkwitherfrown 4, the fusion of atropic acid with potassium hydroxide Winkwitherfrown 5, the action of alcoholic potash upon chlorophenylacetylene Winkwitherfrown 6, the action of benzoyl peroxide upon phenylacetylene Winkwitherfrown 7, the alkaline hydrolysis of triphenylfluoroglycinol Winkwitherfrown 8, the action of ammonium sulfide upon acetophenone Winkwitherfrown 9, the heating of phenylmalonic acid Winkwitherfrown 10, the hydrolysis of phenylacetoacetic ester Winkwitherfrown 11, the action of hydriodic acid upon mandilonitrile 12. 1A and 96, 247, 1855, BR 14, 1645, 1881, Compte Laurent 151, 236, 1910. 2A BR 19, 1950, 1886. 3A BR 44, 537, 1911. 1 and 370, 371, 1909A. 2 Chem 2 1, 443, 1865, BR 14, 239, 1881. 3 BR 10 847, 1877. 4 J. Pract. Chem 282, 52, 58, 1910. 5 and 148, 242, 1868. 6 and 308, 318, 1899. 7 J. Russ. Phys. Chem. SOC 42, 1387, 1910, Chem. Center. 1911, I. 1279. 8 and 378, 263, 1911. 9 BR. 21, 534, 1888, J. Pract. Chem. 281, 384, 1910. 10 BR. 27, 1894. 11 BR. 31, 3163, 1898. 12. Inaugural dissertation of A. Kohler, 1909, University of Bern. 18 phenylacetylene. C6H5CH equals CHBr plus Co. C6H5CTBCH plus KBr plus H2O. Prepared by John C. Hessler. Checked by J. B. Conant and E. R. Barrett. 1. Procedure. In a 500 cubic centimeters Pyrex distilling flask are placed 150 g of potassium hydroxide. The mouth of the flask is provided with a one-hole stopper holding a dropping funnel. The side tube of the flask is connected with a condenser set for downward distillation. The bibromostyrene, 100 g, is placed in the dropping funnel. The distilling flask is gradually heated in an oil bath until the temperature of the bath is 200 feet 0 inches, and the bromostyrene is then dropped in upon the molten potassium hydroxide, at the rate of somewhat less than a drop a second. Since the boiling point of phenylacetylene is 142-143 foot 0, and that of bromostyrene is 218-220, the phenylacetylene distills away from the unchanged bromostyrene. While the bromostyrene is being dropped in, The temperature of the oil bath is raised very gradually to 215-220 and is kept at this temperature until all the bromostyrene has been added. Finally, the temperature is raised to 230 feet 0 inches and is held there until no more distillate comes over. The distillate is colorless. It consists of 2 layers, the lower one being water. The upper layer is separated and dried with solid potassium hydroxide. It is then distilled. The yield of the distilled phenylacetylene, boiling at 142-144 0, is 37 g, 67% of the theoretical amount. 2. Notes. Toward the end of the reaction, a crust of potassium bromide may tend to cover the melted potassium hydroxide. One can break the crust by shaking the distilling flask gently, or by using a glass rod inserted through a second hole in the stopper holding the dropping funnel. It is convenient to have such a rod or stirrer passing through a mercury seal in the stopper of the flask. An occasional turn of this stirrer breaks the crust and facilitates the operation. Mechanical stirring should not be employed, as it reduces the yield tremendously. Apparently, this is because it facilitates the solution of bromostyrene in the tarry byproducts, and thus causes it to polymerize instead of reacting with the potassium hydroxide. A single Pyrex flask can be used for only 3 or 4 runs. The flask should be emptied while still very hot. The yield of material can be somewhat increased by working with small lots, 25 g, of bromostyrene. The use of steel or copper vessels in place of a glass flask seems to diminish the yield slightly. 3. Other methods of preparation. Phenylacetylene has been prepared by the elimination of carbon dioxide from phenylpropiolic acid by means of phenol, 1, or aniline, 2, or by heating with barium hydroxide Wink-Witherfrown 3, from styrene dibromide, by heating with potassium hydroxide and alcohol Wink-Witherfrown 4, by heating B-bromo or chlorostyrene with sodium ethylate or potassium hydroxide and alcohol Wink-Witherfrown 5, by passing the vapors of A-dichloroethylbenzene over hot soda lime Wink-Witherfrown 6, by the action of alcoholic potassium hydroxide on dibenzylacetone tetrabromide Wink-Witherfrown 1b, by the action of aqueous potassium hydroxide on phenylpropargylaldehyde Wink-Witherfrown 2b, by the action of molten potassium hydroxide on B-bromostyrene, 3b. 1 Br. 20, 3081, 1887. 2. Rec Travel Chim. 16, 157, 1896. 3 Arm. 221, 70, 1883. 4, and 154, 155, 1870, 235, 13, 1886, Bull. SOC Chim. 35, 55, 1881, 3, 25, 309, 1901. 5, and 308, 265, 1899, 342, 220, 1905. 6 Jars. 1876, 308, Gaz. Chim. Idle 22, 2, 67, 1892, Bull. SOC Chim. 3, 25, 309, 1901. 1B Br. 39, 41, 46, 1900. 2B Br. 31, 1023, 1898. 3B J. M. Chem. SOC 44, 425, 1922. 19 Phenylhydrazine. C6H5NH2.HCl plus nano 2 plus HCl. C6H5NCl plus NaCl plus 2H2O C6H5NCl plus 4H. Na 2 so 3. C6H5NH2.HCl. Prepared by G. H. Coleman. Checked by J. B. Conant and H. R. Thompson. 1. Procedure. In a 12L, round-bottom flask, fitted with a mechanical stirrer, are placed 1,045 cubic centimeters of concentrated commercial hydrochloric acid, SPGR 1.138. The flask is surrounded with a freezing mixture of ice and salt, and when the contents are at 0 feet 0 inches, stirring is started and 500 g of cracked ice are added, then 372 g of aniline, also cooled to 0 feet 0 inches, are run in during 5 minutes. The mixture is treated with 500 g more of cracked ice, and a cold solution, 0 feet 0 inches, of 290 g of technical sodium nitrite dissolved in 600 cubic centimeters of water are allowed to run in slowly, 20 to 30 minutes, from a dropping funnel, the end of which is drawn to a small tip and reaches nearly to the bottom of the flask. During this addition, the stirrer is operated rather vigorously, and the temperature is kept as near 0 feet 0 inches as possible by the frequent addition of cracked ice, about 1 kilogram. In the meantime, a sodium sulfite solution is prepared by dissolving 890 g of sodium hydroxide, of about 90% purity, in about 1 L of water and then diluting to 6 L. A few drops of phenolphthalein solution are added and sulfur dioxide passed in, first until an acid reaction is indicated and then for 2 or 3 minutes longer. During the addition of the sulfur dioxide, the solution is cooled with running water. On account of the strong alkaline solution, the original color produced by the phenolphthalein is very faint, but this slowly increases until it becomes deep just before the acid point is reached. It is best to remove a small sample of the liquid from time to time, dilute with 3 or 4 volumes of water, and add a drop more of phenolphthalein. The sodium sulfite solution is placed in a 12 L flask and cooled to about 5 feet 0 inches. Approximately 500 g of cracked ice are added, and then, with mechanical stirring, the diazonium salt solution is run in as rapidly as possible. The mixture becomes a bright orange red. The flask is now warmed to about 20 feet 0 inches on a steam bath, until the solid sodium sulfite, which has separated while cooling, redissolves. The total amount of liquid is now about 10 L. 1/2 of this is poured into another 12 L flask, and both halves are warmed on the steam bath to 60-70 foot 0, until the color becomes quite dark, 30 to 60 minutes. Sufficient hydrochloric acid, 300 to 400 cubic centimeters, is now added to each flask to make the solutions acid to litmus. The heating is continued and the color gradually becomes lighter until, after 4 to 6 hours, the solutions have become nearly colorless. They may be heated overnight, if desired. To the hot solutions are now added about 1/3 of their volume of concentrated hydrochloric acid, 2L, to each portion, and the mixtures cooled, first in running water, then in a freezing mixture, to 0 feet 0 inches. The phenylhydrazine hydrochloride precipitates in the form of slightly yellowish or pinkish crystals which may be filtered off and dried. The free base is liberated by adding to the phenylhydrazine hydrochloride 1L of a 25% solution of sodium hydroxide. The phenylhydrazine separates and is taken up with benzene, 300 cubic centimeters, portions. The combined extractions are well dried with 200 g of solid sodium hydroxide, poured off, and distilled. Most of the benzene may be distilled under ordinary pressure, and the remainder, and any low boiling impurities, under diminished pressure. The pure phenylhydrazine boils at 137-138 foot 0/18 mm, and is obtained as a pale yellow liquid. It can be crystallized on cooling in an ice bath. The crystals melt at 230. The crude phenylhydrazine from 2 lots of aniline, 744 g, is best distilled at one time and gives 695 to 725 g of pure product, 80 to 84% of the theoretical amount. 2. Notes. If the sodium sulfite solution contains an excess of alkali, a black tar tends to form when the solution is warmed, and very little phenylhydrazine is obtained. Great care must be taken in determining the end point in the neutralization of the sodium hydroxide by the sulfur dioxide. If the sodium sulfite diazonium salt mixture is acidified before warming or before becoming dark, the red color of the solution does not disappear on heating, and the precipitated phenylhydrazine hydrochloride obtained is colored red. The benzene solution of phenylhydrazine should be well dried before distilling, since the presence of moisture causes an increased amount of foaming to take place just after the benzene has distilled off. When the distillation is carried out carefully, practically no phenylhydrazine distills with the benzene, or other low-boiling impurities. In order to obtain the maximum yield, it is necessary to cool the hydrochloric acid solution of the phenylhydrazine hydrochloride from 20 feet 0 inches to 0 feet 0 inches, before filtration. From 5 to 10% of product separates between these two temperatures. When this is done, no more phenylhydrazine hydrochloride is obtained by concentration of the mother liquor. An increase in the amount of hydrochloric acid above 2L. For the precipitation of the hydrochloride produces no increase in yield of product. Most published directions for the preparation of phenylhydrazine specify the use of zinc dust and acetic acid following the reduction with sodium sulfite. No improvement in the quality or quantity of the product was obtained by using zinc and acetic acid. It is best to use freshly prepared sodium sulfite for the reduction, since the commercial quality is poor and gives a lower yield of phenylhydrazine. A cylinder of liquid sulfur dioxide should, of course, be available. The rapid addition of the diazonium salt solution to the sodium sulfite seems to be advantageous. Pure phenylhydrazine dissolves in dilute acetic acid to yield a perfectly clear solution. The phenylhydrazine hydrochloride may be purified by crystallizing from water. A 600 cubic centimeters portion of water is used for 100 g of crude hydrochloride, and the solution boiled a short time with a few grams of animal charcoal. After filtering, 200 cubic centimeters of concentrated hydrochloric acid are added, and the mixture cooled to 0 feet 0 inches. Pure white crystals in a yield of 85 to 90 g are obtained. Rubber gloves should be worn when working with large quantities of phenylhydrazine, since the product may cause serious injury to the skin. The vapors of phenylhydrazine should not be inhaled. 3. Other methods of preparation. Phenylhydrazine has been prepared by the reduction of benzene diazonium salts with sulfites Winkworthafrown 1, by the reduction of benzene diazonium chloride with stannous chloride Winkworthafrown 2, by the reduction of benzene diazonium hydrate with zinc or sulfur dioxide Winkworthafrown 3, by the reduction of sodium benzene diacetate with sodium stannite Winkworthafrown 4, by the reduction of diazoaminobenzene Winkworthafrown 5, by the reduction of nitrosaphenylhydroxylamine or its methyl ether Winkworthafrown 6, and by the action of hydrazine hydrate on phenol. 7. 1 and 190, 79, 38, 78, br. 20, 2463, 1887. 2 br. 16, 2976, 1883, 17, 572, footnote, 1884. 3 br. 31, 346, 1898. 4 br. 36, 816, 1903. 5 br. 31, 582, 1898. 6 and 190, 77, 1878. 7 br. 31, 2910, 1898. The most feasible method consists in the reduction of diazonium salts with sodium sulfite. Although this method is given in several laboratory manuals, the results were not found entirely satisfactory. The present directions provide for a lengthy but essential heating of the diazonium sulfite mixture, omit the useless zinc dust reduction, and supply exact details for preparation on a fairly large laboratory scale. XX. Phthalimide co C6H4O plus NH4O, C6H4NH plus 2H2O co 2 C6S less than H less than S4O plus, NH4, 2 co 3, 2 C6H4NH plus co 2 plus 3H2O co. Prepared by W. A. Noyes and P. K. Porter. Checked by H. T. Clark and J. H. Bishop. 1. Procedure. In a 5L round-bottom flask, Pyrex, is placed a mixture of 500 g of phthalic anhydride and 400 g of 28% ammonium hydroxide. The flask is fitted with an air condenser not less than 10 mm in diameter and is then slowly heated with a free flame until the mixture is in a state of quiet fusion at a temperature of about 300 feet 0 inches. It requires about 1 hour before all the water has gone and about 1.5 to 2 hours before the temperature of the reaction mixture reaches 300 feet 0 inches and the mixture is a homogeneous melt. It is advisable, during the heating, to shake the flask occasionally. Some material sublimes into the condenser and must be pushed down with a glass rod. The hot reaction mixture is now poured out into a crock, covered with a paper to prevent loss by sublimation, and allowed to cool. The product is practically pure without further treatment, and melts at 232-235 foot 0. The yield is 470 to 480 G, 94 to 95% of the theoretical amount. Phthalimide may also be made by using 500 G of phthalic anhydride and 500 G of ammonium carbonate which has been previously ground in a mortar. The subsequent procedure is the same as when aqueous ammonia is used. Frequent shaking is necessary, and the sublimed material must be occasionally pushed back into the reaction flask. About 2 hours are required for completion. 2. Notes. Several smaller runs of 25 G of phthalic anhydride gave the same percentage yield. Phthalimide may be recrystallized from water, but only about 4 G of phthalimide will dissolve in a liter of boiling water. It may also be crystallized from alcohol, in which solvent it dissolves to the extent of 5 parts in 100 at boiling temperature. On a large scale, it would be advisable to collect the small amount of ammonia given off during the reaction. If desired, the product obtained by pouring the reaction mass into the crock may be treated with hot water to soften the cake, broken up with a glass rod, transferred to a flask and boiled with water for a few minutes. This treatment, however, is quite unnecessary. For all practical purposes, the crude cake, as it is obtained, may be ground up and used directly. 3. Other methods of preparation. Phthalimide has been formed by heating ammonium phthalate with a 1, by heating acid ammonium phthalate with a 2, by passing dry ammonia over heated phthalic anhydride with a 3, by treating phthalochloride with dry ammonia with a 4, by heating phthalimide with a 5, by heating phthalic anhydride with ammonium thiocyanate with a 6, by heating phthalic anhydride with urea with a 7, by heating phthalic anhydride with ammonium carbonate with a 1b, by heating phthalic acid with nitriles with a 2b, by fusing O-cyanobenzoic acid with a 3b, and by the action of potash on O-cyanobenzaldehyde, 4b. 1 jars. 1868, 549, and 19, 47, 1836, 41, 110, 1842, 42, 220, 1842, 205, 300, 1880, 215, 181, 1882. 2 jars. 1847 to 1848, 590. 3 m. Chem. J. 3, 29, 1881. 4 m. Chem. J. 3, 28, 1881. 5 br. 39, 2278, 1906. 6 br. 19, 1398, 1886. 7 br. 10, 1166, 1877, am. Chem. J. 18, 333, 1896, J. am. Chem. SOC 32, 116, 1910, Z. Enju. Chem. 32, I. 301, 1919. 1B J. M. Chem. SOC 42, 1282, 1920. 2B J. M. Chem. SOC 18, 680, 1896, 20, 654, 1898. 3B Rec Travel Chim. I. 11, 93, 1892. 4B BR. 30, 1698, 1897. Of these, the first 3 are the only ones which need be considered as methods for the preparation of phthalimide. It was found that the third was by no means easy to bring about. Dry phthalic anhydride is apparently only superficially affected by the dry ammonia, and it was difficult to introduce sufficient heat into the loose mass of crystals to cause the reaction to start. 21 quinoline / //C3H5 O3 plus C6H5 NH2 plus 4O C6H5 NO2 plus 4H2O // N/. Prepared by H. T. Clark and N.W. Davis. Checked by Roger Adams and A. W. Sloan. 1. Procedure. In a 5L, round-bottom flask, fitted with an efficient reflux condenser of wide bore, are placed, in the following order: 80 g. of powdered crystalline ferrous sulfate, 865 g. of glycerol, C.P. 218 g. of aniline, 170 g. of nitrobenzene, and 400 cubic centimeters of concentrated sulfuric acid, SPGR 1.84. The contents of the flask are well mixed, and the mixture heated gently over a free flame. As soon as the liquid begins to boil, the flame is removed, since the heat evolved by the reaction is sufficient to keep the mixture boiling for 1/2 to 1 hour. If the reaction proceeds too violently at the beginning, the reflux condenser may be assisted by placing a wet towel over the upper part of the flask. When the boiling has ceased, the heat is again applied and the mixture boiled for 5 hours. It is then allowed to cool to about 100 feet 0 inches and transferred to a 12L flask. The 5L flask is rinsed out with a small quantity of water. The 12L flask is then connected with the steam distillation apparatus shown in Figure 3, a 12L flask being used as a receiver. Steam is passed in, without external heat, until 1500 cc have distilled, 10 to 30 minutes. This removes all the unchanged nitrobenzene, 10 to 20 cubic centimeters. The current of steam is then interrupted, the receiver is changed, and 1500 g. of 40% sodium hydroxide solution are added cautiously through the steam inlet. The heat of neutralization is sufficient to cause the liquids to boil, and thus become thoroughly mixed. Steam is then passed in as rapidly as possible until all the quinoline has distilled. In this process, 6 to 8 L of distillate are collected. 2.5 to 3.5 hours are required, unless a very efficient condensing apparatus is used, under which conditions the distillation may be complete in 1/2 to 1.5 hours. The distillate is allowed to cool, and the crude quinoline separated. The aqueous layer of the distillate is again distilled with steam until all the quinoline has been volatilized and collected in about 3 L of distillate. These 3 L of distillate are then mixed with the first yield of quinoline and 280 g. 150 cubic centimeters of concentrated sulfuric acid are added. The solution is cooled to 0-5'0", and a saturated solution of sodium nitrite added until a distinct excess of nitrous acid is present, as shown either by starch potassium iodide paper or by the odor. This generally requires 50 to 70 g. of sodium nitrite. The mixture is then warmed on a steam bath for an hour, or until active evolution of gas ceases, and is then distilled with steam until all the volatile material has been expelled. 41 of distillate will result. The receiver is then changed and the mixture in the distillation flask is neutralized, as before, with 700 g. of 40% sodium hydroxide solution. The quinoline is distilled exactly as described above, the aqueous portions of the distillate being distilled with steam until all the quinoline has been isolated. The crude product is then distilled under reduced pressure, and the fraction which boils at 110-114 foot 0/14 mm is collected. The foruns are separated from any water which may be present, dried with a little solid alkali, and redistilled. The total yield is 255 to 275 g, 84 to 91% of the theoretical amount based on the aniline taken. 2. Notes. Although these directions have been used many times with results exactly as described, in a few cases the yields have dropped to 60 to 65% without any apparent reason. At present no explanation can be given for this. In the Scrope synthesis of quinoline, the principal difficulty has always been the violence with which the reaction generally takes place. It occasionally proceeds relatively smoothly, but in the majority of cases gets beyond control, with consequent loss of material through the condenser. By the addition of ferrous sulfate, which undoubtedly functions as an oxygen carrier, the reaction is extended over a longer period of time. It is thus possible to work with much larger quantities of material when ferrous sulfate is employed. It is important that the materials should be added in the correct order. Should the sulfuric acid be added before the ferrous sulfate, the reaction may start at once. It is also important to mix the materials well before applying heat. The aniline sulfate should have dissolved almost completely, and the ferrous sulfate should be distributed throughout the solution. To avoid danger of overheating, it is well to apply the flame away from the center of the flask where any solids would be liable to congregate. In the apparatus for steam distillation, the greater portion of the condensation is effected by the stream of water passing over the receiver. It is, therefore, necessary that the stream passing through the condenser should be sufficiently rapid to cause it to form a uniform film over the receiving flask. A 12L flask is even more efficient as a condenser than the 5L flask. It is important that the tube through which the vapors leave the distillation flask should be either too short nor, especially, too narrow. Where the external diameter of the steam inlet tube is 5 to 8 mm, the internal diameter of this steam head should be not less than 28 mm. Were it less, the current of steam passing through it would be so rapid as to prevent small quantities of liquid from returning to the flask, and these would be driven over into the receiver. Much time can be saved by the use of the steam distillation apparatus described, especially when large quantities have to be handled. The above directions avoid the use of extraction methods, which not only consume more time but may lead to appreciable losses of material. If the downward condenser is of iron, the apparatus is even more efficient, and the time for the steam distillation is halved. The percentage yields have been based on the amount of aniline taken. It would probably be more legitimate to base the calculation on the amounts of aniline taken and of nitrobenzene not recovered, since undoubtedly the latter is reduced to aniline during the course of the reaction. If this be done, the yield is found to be only 55 to 60% of the calculated amount. In a number of experiments, the glycerol used contained an appreciable amount of water. Under these conditions, the yield of product is much lower. Dynamite, glycerol containing less than 0.5% of water is best employed. U.S.P. Glycerol contains 5% of water and usually gives lower yields. 3. Other methods of preparation. Quinoline has been produced by passing the vapor of allylanilene over red-hot lead oxide Winkworth-Fraun 1A, by heating acrylidinianiline, or better, a mixture of aniline, glycerol and sulfuric acid Winkworth-Fraun 2A, by heating aniline with glycerol and sulfuric acid, using nitrobenzene as an oxidizing agent Winkworth-Fraun 1. By treating a mixture of glyoxyl and O-toluidine with alkali Winkworth-Fraun 2. By treating a solution of O-aminobenzaldehyde with acetaldehyde and alkali Winkworth-Fraun 3. By heating methylacetanilide with zinc chloride Winkworth-Fraun 4. By heating aminoazobenzene with glycerol and sulfuric acid Winkworth-Fraun 5. By heating a mixture of aniline, glycerol and sulfuric acid with arsenic acid. 6. 1A Br. 12, 453, 1879. 2A Br. 13, 911, 1880, Monich. 1, 316, 1880. 1 Monich. 2, 141, 1881, J. Pracht. Chem. 2, 49, 549, 1894. 2 Monich. 15, 277, 1894. 3 Br. 15, 2574, 1882, 16, 1833, 1883. 4 Br. 23, 1903, 1890. 5 Br. 24, 2623, 1891. 6 Br. 29, 704, 1896. Of the above methods, the only ones which need be considered are those in which a mixture of aniline, glycerol and sulfuric acid is heated with an oxidizing agent. With the use of nitrobenzene, the reaction, according to the original method, takes place with extreme violence. The method above described is the most satisfactory for the preparation of quinoline itself, but for the preparation of homologues of quinoline, the use of arsenic acid is preferable, since the yields are somewhat greater. Since the work was carried out, a method has been published, 7, in which aniline, glycerol, and sulfuric acid are treated with ferric oxide. By this method, Adams and Parkes were unable to obtain yields comparable with those resulting from the above directions. 7 Chem. News 121, 205, 1920. 22 Quinone. 1. Hox 6H4O4 plus O, Na 2 Cr2O7 plus H2SO4, O equals C6H4 equals O plus H2O, prepared by E. B. Vliet. Checked by Roger Adams and E. Dreger. 1. Procedure. In a 2.5 L beaker, 100 g of hydroquinone are dissolved in 2000 cc of water heated to about 50 feet 0 inches. After the solid is completely dissolved, the solution is cooled to 20 feet 0 inches, 100 g of concentrated sulfuric acid are slowly poured in, and the mixture is again cooled to 20 feet 0 inches. A concentrated solution of technical sodium dichromate is prepared by dissolving 140 g in 65 cubic centimeters of water. This solution is then added gradually to the hydroquinone solution, with the use of a mechanical stirrer, see notes, the mixture being cooled so that the temperature never rises above 30 feet 0 inches. At first a greenish-black precipitate forms, but upon further addition of the sodium dichromate solution, the color changes to yellowish-green. As soon as this color remains permanent, a slight excess of sodium dichromate does no harm, the reaction is complete. This requires about 1/2 to 3/4 of an hour, 90 to 110 cubic centimeters, of sodium dichromate solution is necessary. The mixture is then cooled to about 10 feet 0 inches and filtered with suction. As much water as possible is pressed out of the crystals. The filtrate is extracted twice, 150 cubic centimeters of benzene being used for each extraction. The precipitate of quinone is transferred to a 1L beaker, and 500 cubic centimeters of benzene, including the 300 cubic centimeters used to extract the filtrate, are added. The mixture is now heated with stirring on a steam bath, and as soon as most of the quinone has dissolved, the benzene layer is decanted into another beaker. It is dried while hot by stirring a short time with a little calcium chloride, and then filtered through an ordinary funnel into a 1L distilling flask before it cools. There is a certain amount of quinone which does not go into the 500 cubic centimeters of benzene, so that the residue is extracted a second time with about 100 cubic centimeters of benzene, which is dried and filtered with the first extract. During these extractions, the benzene should not be at the boiling point, as this will cause a considerable volatilization of the quinone. The distilling flask is now attached to a condenser set for downward distillation, and the benzene is distilled. As soon as the quinone starts to separate, the residue in the flask is transferred to a beaker and cooled in an ice bath. The precipitate is filtered off with suction and the product spread out for a short time to dry. The product is yellow in color and weighs 75 to 80 g, 76 to 81% of the theoretical amount. Material made in this way will hold its yellow color over long periods of time, provided it is protected from light. The benzene distillate is yellow and contains some quinone. This, as well as the benzene from the final filtration of the quinone crystals, may be used in a subsequent run and thus raises the yield of the subsequent runs to about 85 to 90 g, 85 to 90% of the theoretical amount. 2. Notes. As the mixture becomes thick during the oxidation, it is very necessary to use a stirrer which will keep the whole mass agitated by reaching to the sides and bottom of the beaker. If impure hydroquinone is used, a black, sticky precipitate will usually appear after the addition of the sulfuric acid to the hydroquinone solution. This should be removed before the oxidation is started by filtration without suction through a fluted filter. When technical sodium dichromate is used, the solution should be filtered with suction before it is added to the hydroquinone, in order to remove any insoluble impurities. In the laboratory, it is convenient to make several small runs of the size indicated, as far as the oxidation is concerned, but the benzene extractions can be combined. It is also possible to obtain good yields of quinone in the following manner. 1,500 cubic centimeters. Of water, 465 g. Of concentrated sulfuric acid and 300 g. Of hydroquinone are mixed in a 3L beaker. The mixture is cooled to 0 feet 0 inches, and 330 g. Of sodium dichromate are added in powdered form, the temperature being kept below 5 feet 0 inches at all times. This procedure requires a longer time and much more care in the control of conditions than the method described above. 3. Other methods of preparation. Quinone may be prepared by the oxidation of aniline with dichromate or manganese dioxide and sulfuric acid. 1. This is a more feasible commercial method than the one given. However, the oxidation of hydroquinone is more rapid and convenient, and, hence, is more desirable for use in the laboratory. Various materials have been oxidized by chemical means to give quinone. They are quinic acid, 2. Hydroquinone, 3. Benzidine, 4. P-phenylenediamine, 5. Sulfonilic acid, 6. P-phenylsulfonic acid, 7. Arbutin, 8. Aniline black, 9. And the leaves of various plants. 10. Quinone is also formed by several other methods: by the fermentation of fresh grass winkwitherfrown 11. By the action of iodine on the lead salt of hydroquinone winkwitherfrown 1b. By the decomposition of the compound C6H4.2-Cro2Cl with water winkwitherfrown 2b. By the action of sulfuric acid on phenol blue winkwitherfrown 3b. By the electrochemical oxidation of aniline, 4b, hydroquinone, 5b, or benzene winkwitherfrown 6b, by the catalytic oxidation of benzene, 7b. 1 Jars. 1863, 415, br. 10, 1934, 2005, 1877, 16, 687, 1883, 19, 1468, 1886, 20, 2283, 1887, 31, 1524, 1898, and 200, 240, 1880, 215, 127, 1882, 2, and 27, 268, 1838, 3 and 51, 152, 1844, J.M. Chem. J. 14, 555, 1892, 4 Jars. 1863, 415, 5 Jars. 1863, 422, 6 and 159, 7, 1871, br. 8, 760, 1875, 7 br. 8, 760, 1875, 8, and 107, 233, 1858, 9 br. 10, 1934, 1877, 34, 1285, 1901, 10, and 89, 247, 1854, br. 34, 1162, 1901, 11 br. 30, 1870, 1897, 1b br. 31, 1458, 1898, M. Chem. J. 2620, 1901, 2b and Chim. Phys. 5, 22, 270, 1881, 3b br. 18, 2915, 1885, 21, 889, 1888, 4b d. r. p. 109,012, FRDL. 5, 664, 1900, d. r. p. 117,129, FRDL. 6, 112, 1901, J. SOC Dyers and Colorists, 36, 138, 1920. 5b d. rp. 117,129, FRDL. 6, 112, 1901. 6b d. r. p. 117,251, FRDL. 6, 109, 1901, U.S. Pat. 1,322,580, 1919, ca. 14, 287, 1920, Rev. Projects Jim. 21, 219, 1918, 21, 288, 1918. 7 B.U.S. Pat. 1,318,631, 1919, ca. 14, 70, 1920. 23. Sodium p-toluenesulfonate. 2CH3C6H4SO2Cl plus 3ZN, CH3C6H4SO2, 2ZN plus ZnCl2, CH3C6H4SO2, 2ZN plus Na2CO3, 2CH3C6H4SO2 Na plus Senco3. Prepared by Frank C. Whitmore and Francis H. Hamilton, checked by J. B. Conant and Paul Allen, Jr. 1. Procedure. 500 grams of technical p-toluene sulfonyl chloride are ground in a mortar to break up all lumps. 3 liters of water are placed in a 12L crock provided with a large brass stirrer and a tube for passing steam directly into the liquid. Dry steam is passed into the water until the temperature reaches 70 feet 0 inches. The steam is then shut off and 400 g of zinc dust, 90 to 100% pure, is added. The sulfonyl chloride is then added in small portions by means of a porcelain spoon. The addition takes about 10 minutes. The temperature rises to about 80 feet 0 inches. Stirring is continued for 10 minutes after the last of the chloride has been added. Steam is then passed into the mixture until the temperature reaches 90 feet 0 inches. If it is heated any hotter, bumping takes place. The steam is shut off, and 250 cubic centimeters of 12N sodium hydroxide solution is added. Finely powdered sodium carbonate is then added in 50 g portions until the mixture is strongly alkaline. The mixture froths considerably, but this causes no trouble unless too small a crock is used. The stirrer is loosened and the crock is removed. The mixture is filtered by suction in a large funnel. The filtrate has a volume of about 4.5 L. The cake of unchanged zinc dust and zinc compounds is transferred to a 3L battery jar and placed under the stirrer, and the latter is clamped in place. Water, 750 cubic centimeters, is added, the stirrer is started, and steam is passed in until the mixture starts to froth too violently. The steam is then shut off, but the stirring is continued for 10 minutes. The mixture is filtered and the filtrate is added to the main solution in a large evaporating dish. The liquid is evaporated over a large burner to a volume of about 1 L, or until a considerable crust forms around the edges. The mixture is then cooled. Large, flat, transparent crystals separate. The thoroughly cooled mixture is filtered by suction, and the crystals are air-dried until efflorescence just starts. They are then bottled. The product is CH3C6H4SO2NA.2H2O. Yield 360 g, 64% of the theoretical amount. Careful acidification of the mother liquor with dilute hydrochloric acid yields 15 g of the free sulfonic acid. 2. Notes. The free sulfonic acid may be prepared by dissolving the sodium salt in cold water and carefully acidifying the solution with hydrochloric acid. An excess of the latter must be avoided, as it dissolves the acid to a certain extent. The sulfonic acid is difficult to dry without partial conversion into the sulfonic acid. 3. Other methods of preparation. Toluenesulfonic acid and its salts have been prepared by 3 general methods. 1. The reduction of the sulfonyl chloride. The reagents which have been used for this are sodium amalgam, 1. Zinc dust and alcohol or water, 2. Sodium sulfite, 3. Sodium sulfide, 4. Potassium hydrosulfide, 5. The thioacid being first formed, and sodium arsenite. 6. 2. From toluene by the Friedel and Crafts reaction, using either sulfur dioxide and hydrogen chloride 7, or sulfuryl chloride 8. 3. From p-toluidine by diazotization and subsequent treatment with sulfur dioxide and finely divided copper. 1b. The compound has also been obtained in certain reactions which, however, would not be suitable for preparative work. Thus it is formed by hydrolysis and reduction of certain thiode derivatives, 2b, prepared from the acid itself, and also by the decomposition of diethylyl sulfone methylamine, 3b. 1 and 142, 93, 1867. 2 Br. 9, 1586, 1876. 3 Br. 3, 965, 1870. 4 D. R. P. 224,019, Chem. Center. 1910-2, 513. 5 Br. 42, 3821, 1909. 6 Br. 41, 3351, 1908, Br. 42, 480, 1909. 7 Br. 41, 3318, 1908, J. Chem. SOC 93, 754, 1908. 8 Rec Travel Chim. 2 30, 381, 1911. 1 B Br. 32, 1141, 1899, J. Chem. SOC 95, 344, 1909. 2 B Br. 15, 130, 1882, 20, 2088, 1887, 41, 3351, 1908. 3 B J. Pract. Chem. 2 63, 170, 1901. 24 1, 3, 5 trinitrobenzene. C6H2, No 2, 3 Co2H, C6H3, No 2, 3 plus Co2. Prepared by H. T. Clark and W. W. Hartman. Checked by J. B. Conant and J. J. Toohey. 1. Procedure. The crude trinitrobenzoic acid obtained by oxidation of 360 G of trinitrotoluene, Prep. 25, page 95, is mixed with 2L of water at 35 feet 0 inches in a 5L flask provided with a stirrer. 15% sodium hydroxide solution is added, with continuous stirring, until a faint red color is just produced. See notes. The color is then immediately discharged by means of 1 or 2 drops of acetic acid, and the liquid is filtered from unchanged trinitrotoluene. The filtrate is transferred to a 5L flask, and 70 cubic centimeters of glacial acetic acid are added. The mixture is then gently heated, with continuous stirring, when trinitrobenzene separates in crystalline condition and floats on the surface of the liquid as a frothy layer. After about 1.5 hours, the evolution of gas ceases. At this point, the crystals begin to stir into the solution. The heating and stirring is continued for 3/4 of an hour, when the mixture is allowed to cool, and the crystals filtered off. A sample of the filtrate should be tested for undecomposed trinitrobenzoic acid. If a precipitate is produced by the addition of sulfuric acid, the process must be continued. After recrystallization from glacial acetic acid, the product melts at 121-122 foot 0. The yield is 145 to 155 G, 43 to 46% of the theoretical amount calculated from the trinitrotoluene. 2. Notes. During the solution of the trinitrobenzoic acid, the temperature should not be below 35 feet 0 inches, owing to the slight solubility of trinitrobenzoic acid in cold water. The heat of neutralization raises the temperature to 45-55 foot 0, but the latter temperature should not be exceeded, since any trinitrobenzene formed at this point would later be removed with the unreacted trinitrotoluene. Care must be taken that no more alkali is added than is just sufficient to produce the faint red color. If an excess of alkali is added, it produces a permanent color, which is not removed by acid and colors the final product. When once the evolution of carbon dioxide sets in, the flame must be cut down so as to avoid the formation of a thick layer of froth which might foam over. 3. Other methods of preparation. 1. 3. 5-trinitrobenzene can be prepared by heating M-dinitrobenzene with nitric acid and sulfuric acid to 120 foot 0 wink with a frown 1. By heating 2. 4. 4,6-trinitrotoluene with fuming nitric acid in a sealed tube at 180 feet 0 inches for 3 hours. Wink with a frown. 2. By heating 2,4,6-trinitrobenzoic acid or its sodium salt with water, alcohol, dilute sodium carbonate or other suitable solvent. 3. 1 Br. 9, 402, 1876, and 215, 344, 1882. 2 Br. 16, 1596, 1883. 3 D. R. P. 77,353, FRDL. 434, 1894. 25 2, 4, 6-trinitrobenzoic acid. C6H2, No2, 3CH3 plus 3O, Na2Cr2O7 plus H2SO4, C6H2, No2, 3CO2H plus H2O. Prepared by H. T. Clark and W. W. Hartman. Checked by J. B. Conant and J. J. Toohey. 1. Procedure. To 3,600 g of concentrated sulfuric acid in a 5L flask placed in an empty water bath are added 360 g of technical trinitrotoluene, while the mixture is stirred mechanically. Sodium dichromate, Na2Cr2O72H2O, is now added in small quantities, precaution, see notes, with constant stirring, until the temperature of the mixture reaches 40 feet 0 inches. The empty water bath is now filled with cold water and the addition of sodium dichromate continued at such a rate that the temperature remains at 45-55 foot 0. In all 540 g of sodium dichromate are added, the addition taking 1 to 2 hours. When all has been added, the mixture, which has now become very thick, is stirred for 2 hours at 45-55 foot 0 and poured into a crock containing 4 kilograms of crushed ice. The insoluble trinitrobenzoic acid is filtered off and carefully washed with cold water until free from chromium salts. On drying, it weighs 320 to 340 g. The product is now mixed with 2L of distilled water at 35 feet 0 inches in a 5L flask provided with a stirrer, and 15% sodium hydroxide solution is dropped in with continuous stirring until a faint red color is just produced. Should this disappear, it is restored by the addition of a few drops more. When it has persisted for 5 minutes, the color is discharged by the addition of a few drops of acetic acid, and the insoluble unattacked trinitrotoluene filtered off and washed with a little water. The trinitrobenzoic acid is precipitated from the filtrate by the addition of a slight excess of 50% sulfuric acid. The solution is chilled, and the acid filtered and washed free from salts with ice water. When dried in air, it weighs 230 to 280 g, 57 to 69% of the theoretical amount. 2. Notes. The mother liquors and washings lose carbon dioxide on boiling, and the insoluble trinitrobenzene separates. See Preparation 24. After filtering, washing, and drying, it weighs 15 to 20 g, 4 to 6% of the theoretical amount. It is essential that the stirring should be most efficient, so that when the mixture becomes thick, the dichromate will be evenly distributed throughout the liquid, as rapidly as it is added. If the stirring is not efficient, local reactions of extreme violence, in certain cases leading to conflagration, will occur. An iron stirrer may be employed in the oxidation reaction, but not in the purification. Technical sodium dichromate generally contains a certain amount of chlorides, and the chlorine liberated from these tends to cause a troublesome foam towards the end of the reaction. Only a very efficient stirrer, which draws down the surface of the liquid, is able to combat this difficulty. The amount of solid sodium dichromate given is for the dry crystalline compound containing 2 molecules of water of crystallization. Great care should be taken in dissolving the crude acid in the alkali. If an excess of alkali persists for any length of time, a permanent color is produced which will discolor the final product. The acid is fairly soluble in cold water and should be washed with care. 3. Other methods of preparation. 2,4,6-trinitrobenzoic acid has been prepared by heating trinitrotoluene with fuming acid in a sealed tube to 100 feet 0 inches for 2 weeks, 1a, the oxidation being only partial. It can also be prepared by heating trinitrotoluene under a reflux condenser, with a mixture of 5 parts of concentrated nitric acid and 10 parts of concentrated sulfuric acid. With the frown 1. This method is, however, unsuitable in the laboratory owing to the difficulty of devising suitable apparatus. Another method is to dissolve trinitrotoluene in nitric acid and to this solution, at 95 feet 0 inches, to add potassium chlorate at such a rate that the temperature does not fall. With the frown 2. This method has been found to be difficult to control on a laboratory scale. 1a Br. 3 223 1870. 1d R. P. 77,559, FRDL. 4 34 1894. 2d R. P. 226,225, FRDL. 10 167 1910. The method described above is a modification of a patented process 3, in which trinitrotoluene suspended in sulfuric acid is treated with chromic anhydride. 3d R. P. 127,325, FRDL. 6 148 1901. A. Acetic acid 18, 33, 64 acetone, 41 acetophenone, 1 ammonium carbonate, 75 ammonium hydroxide, 37, 75 aniline, 71, 79 anthranilic acid, 47. B. Benzylacetophenone, 1 benzaldehyde, 1, 5-benzoic acid, 5-benzyl alcohol, 5-benzobenzoate, 6-benzyl chloride, 9-benzyl cyanide, 9 to 11, 27, 57, 63 bromostyrene, 67. C. Carbon tetrachloride, 23 chlorine, 37 copper sulfate, 38. D. Dibenzyl ether, 6A, G-dichloroacetone, 13 to 15 dimethylaminobenzaldehyde, 17 to 21 dimethylaniline, 17, 47. E. Ethyl alcohol, 23, 27 ethyl oxalate, 23 to 26 ethyl phenylacetate, 27 to 28. F. Ferrous sulfate, 79 formaldehyde, 17. G. Gelatin solution, 37 glycerol, 29, 33, 79 glycerol A, G-dichlorohydrin, 29 to 31 glycerol A monochlorohydrin, 33 to 35. H. Hydrazine sulfate, 3740 hydrochloric acid, 17, 30, 34, 47, 71 hydroquinone, 85. Mesitylene, 41 to 45 methyl red, 47 to 61. N. Naphthol, 61 nitric acid, 57 nitrobenzene, 79 p-nitrobenzoic acid, 63 to 66 p-nitrobenzyl cyanide, 67 to 58, 59 p-nitrophenylacetic acid, 69 40 nitrosodamethylaniline hydrochloride, 17 nitroso-3 naphthol, 61 to 62 nitrotoluene, 53. O. Oxalic acid, 23. P. Phenylacetic acid, 10, 63 to 65 phenylacetylene, 67 to 69 phenylhydrazine, 71 to 74 phthalic anhydride, 75 phthalimide, 778 potassium hydroxide, 67. Q-quinoline, 7983 quinone, 8688S. Sodium acetate, 48 sodium benzylate, 6 sodium cyanide, 9 sodium dichromate, 13, 53, 85, 95 sodium hydroxide, 1, 37, 61, 93 sodium hypochlorite, 37 sodium, metallic, 5, 42. Sodium nitrite, 17, 47, 61, 71, 80 sodium sulfite, 71 sodium p-toluene sulfonate, 91 sulfur dioxide, 71 sulfuric acid, 13, 27, 30. 34, 37, 41, 43, 53, 57, 59, 63, 79, 85, 95. T-toluene, 48 toluene sulfonyl chloride, 89I, 3, estrinitrobenzene, 93, 94, 96 2, 4, 6 trinitrobenzoic acid, 93, 96 97 2, 4, 6 trinitrotoluene, 93, 95 zinc dust, 89,